Good morning. Thank you all for coming at this early hour, and thanks very much to the organizers for inviting me to this conference. I've really enjoyed the other talks that I've heard, and I hope to contribute a grain of sand to the thing today. I think, based on my conversations with Mauro as we walked here today, things I say will be controversial and certainly disputed if we have time for questions, and I will certainly try to leave time for some discussion. So let me get started. I'm going to start with a digression, but it won't take long, which is just something about the way one should do metaphysics based on looking at physical theories. It's something we'd like to do. It makes sense if you have a minimally pro-scientific view of the world to think about what we can learn about nature and its metaphysics from what physics has taught us so far. But the wrong way to do it is to say something like this: our best physical theory of X quantifies over P's and Q's and R's, therefore we should believe in the reality of P's and Q's and R's and believe that they are described just as described in the theory's X models. You will find statements like this from philosophers of physics in the 20th century, but I think it's not the right way to do things because, in general, our best theory is not something that we can or should believe is true. Rather, it's something that gives us hints or intimations about what nature may be like at best, and we have to make our metaphysical morals very cautiously in light of this fact. So I just wanted to say that at the outset. So my topic is whether temporal passage can be considered compatible with the physical theories that are our current best theories. And I want to make clear that I'm talking about the notion of passage of time in exactly the sense that I thought that Yuval was talking about it yesterday, where this is the common sense notion of time as always passing and flowing. The past events recede into the past and we move into the future. The division into past, present, and future is crucial to this understanding of time. And in the now, at least, everything that exists coexists. That is to say, that which exists is not just me here, but also you. In a robust sense, we are all together in this world. And passage affects everything that exists in some sense equally. So this is the notion that I'll be presupposing as our notion of temporal passage. And the crucial fact to take away from this is the idea of coexistence and the idea that we are all together in this now, which means that a kind of a minimal necessary condition for squaring temporal passage with physics is that the physics not tell us that there is no such thing as a privileged way of slicing events into events that are simultaneous with each other and those which are not. So that's the starting point. The familiar tension from relativity theory that I'll get to in a moment. A second digression was prompted by Ellie Doring's talk yesterday. Temporal passage, in the sense I'm talking about it, is indeed a third time, in the sense that he said yesterday there's no such thing. What do I mean? Temporal passage is not the same as experienced time in our minds or our conscious experience. They are not the same thing. And it is not any of the multiple times of special relativity either. So if that's your dichotomy of the two times, which I think is what Eli was talking about yesterday, passage as I'm talking about it is not either of those. I want to maintain that we do not directly perceive the present or simultaneity in experience. Rather, our conscious experience is an ongoing process that's a construction, a constantly renewing construction of our perceptions and our thoughts that's happening in our brains. It's carried out in our brains. And we know a lot about how that construction works due to psychological experiments and studies that go back to the time of James, but have been becoming ever more sophisticated. We know a lot about how the construction of a felt present and the simultaneity that we perceive in the events as we experience them gets carried out in the brain. But, and for example, my friend Craig Callender has a wonderful book called What Makes Time Special that he published a couple of years ago. And in that book, he devotes 2 or 3 chapters to reviewing psychology and cognitive science literature that tries to offer an explanation of how our notion of the present that we perceive and its moving into the future, how that arises in the brain. You can think of that as an attempt to show how temporal passage is illusory. I think that's the way Craig would like us to think of that. But no, you can't think of it that way, because in fact, everything that is said in those chapters about how this process works, what happens in the brain, and then this happens, and then that, and this input is processed through this module, etc. All of those stories presuppose temporal passage in the world, in the objective world where our brains are physical objects. And so they do nothing to convince us, to convince me at least, that passage of time is an illusion. What they do is instead teach us how the internal gets to correlate with and partially reflect the external passage. And it does so imperfectly, but actually pretty darn well, for reasons that are easy to explain evolutionarily. Okay, so that is almost the end of my digression, the second digression. I just want to add that taking temporal passage and the distinction of past, present, and future seriously is not making time into a thing like an ether. The ether made space into a thing. That was one of the things that Eli warned us against yesterday. And it is also not to rule out someday telling a further explanatory story about time and time's passage. Because so far, the nature of the passage of time, even if one is willing to consider that it might be an objective feature of the world, remains quite mysterious. And there are even conceptual arguments that it makes no sense intrinsically, which have some power. And I won't try to answer those arguments today. So what I'm going to be doing is just examining whether passage can be reconciled with physics minimally, in the sense that we can take physics to not rule out the existence of absolute simultaneity, or a preferred frame of reference in the sense of relativity theories. So I'll look at the initial threat to passage that arose from special relativity and Minkowski spacetime. I'll move on to look at general relativity and ask whether it becomes more friendly to the passage of time, or to this minimal necessary condition for the passage of time. And then I'll say a few words about quantum theories and the new considerations that come in with quantum physics, and we won't have time for any more than that. So here's a standard Minkowski diagram showing the typical structure from the perspective of the central point of space-time in special relativity, or Minkowski space-time. So I've illustrated the future light cone and the past light cone, and the most important things for our purposes, well, the light cone structures are very important, and the stuff colored in the back is everything that can causally affect this event in the middle, which we can think of as our here and now. And then if we are at rest in our reference frame, the line going vertically is our path through space-time. And this is what we teach our students is the now in our reference frame. We say something like that, our reference frame. In reality, the reference frames, I think, are minimally important. And in fact, Tim Maudlin has a very nice book that came out a few years ago, teaching relativity and showing you how you can teach it and understand it without talking about reference frames, basically at all. It's a geometric theory. But anyway, people are normally taught to think about reference frames. And then the key factor, of course, is that if we think of this as the line linking all the events that are happening now in our reference frame, then for somebody moving at a substantial fraction of the velocity of light, a quite different set of events would be considered from their perspective the things happening now. And there's a kind of a disagreement. If we cross each other right here, the spaceship whizzes by right outside that window, then we're sort of together in the here and now, but we have very different verdicts about what has happened already and what is still yet to come, which we can illustrate with this kind of diagram. This blue line is the light cone for us here and now on Earth, and here's some friends of ours living on Jupiter, which is basically in the same reference frame as us, basically at rest with respect to the Earth in relativistic terms. But there's some passing astronauts going by at a substantial fraction of the velocity of light. For us, and the people in Jupiter, it's very clear that event B is earlier than event A. It happens before. It might happen, according to our clocks, which are in sync with those on Jupiter, it might happen 4 or 5 minutes before. And yet, to the passing astronauts, using this criterion of simultaneity that matches their reference frame, event A is actually a couple of minutes before event B. And this is the challenge that's supposed to wreck the common sense notion of the passage of time, and the past, present, future distinction. Now, philosophers have dedicated some effort to trying to accept Minkowski's space-time structure and nevertheless rescue some sort of temporal passage or becoming and locate it in Minkowski space-time. And so one of the most popular proposals is illustrated here, where we take this diagonal, this triangular thing is again the backward light cone from here and now, and to say, well, what special relativity teaches us is that passage is as it were, local or relative to a world line. So if this is our world line going up the diagram, then the past is the shaded area, the future is the white, and the present for us we can take to be the edge of the light cone. And I think of this as a kind of an epistemic criterion, because really what the backward light cone consists of are all the events that in an idealized sense we could know about, and that could be affecting us at the moment here and now. So Mauro and Howard Stein and others have said that the lesson of special relativity is you have to relativize your notion of passage of time to a world line like this. Just to mention, there's a different proposal in a recent book by Sven Rosenkrantz and Fabrice Correa, where they take the opposite. They take the future pointing light cone and say that's actually the edge of becoming. And I think that they have a more ontological criterion in mind, which is that all the shaded area now are things that are over and done with as far as we are concerned. Nothing we can do here and now can affect any of the stuff that's shaded there. And so it has the property that we normally ascribe to the past of being fixed, done, and beyond our control. Okay? But for me, both of these proposals don't match the intuitive notion of passage that I described before. It's lonely at the top. And Yuval said something striking about this yesterday. He said, this is really a point-like present and a point-like sense of being in the present where the tip of your nose doesn't even count as being shared with you there. Even if one is willing to relax and fuzz out the point-like nature of the edge of the light cones, it still is unsatisfactory, intuitively speaking, in two senses. One is that we'd like to share the world and not and have a notion of the world as all sort of equally sharing this movement that goes into the future, and it kind of also in a solipsistic or at least very conceited way privileges us here, which doesn't seem very in keeping with the scientific spirit. So these proposals have been made over and over. For people who are fond of traditional temporal passage, they tend not to be satisfactory. And coexistence, again, is the missing key ingredient. If temporal passage in the sense that interests me is to be something that objectively happens, it has to be something that everything that coexists undergoes together without invidious distinctions. And the local or Lorentz invariant versions of passage are too solipsistic and observer relative to be objective features of temporal reality in the sense that I'm interested in talking about. Now, fortunately, Minkowski spacetime is weird, and we have no reason to think that our actual spacetime structure shares all the features that I just described to you. And I'm going to skip talking about this for reasons of time. But Minkowski spacetime is indeed very, very weird. And it isn't the same when you move to general relativity. Special relativity, everybody knows, is incompatible with gravity in the sense that although you can come up with gravity theories that are set in a Minkowski space-time background, they invariably have empirically, obviously false consequences. And that's why we don't look at those theories and we just go straight to general relativity for our gravity theory. But it's interesting, once you do go to general relativity and Einstein's equations, what you find, and this is a key fact I'll be discussing now, there are no models of general relativity that both have matter in the ordinary fermionic sense and have Minkowski space-time structure everywhere, in the sense of rigorously Minkowski space-time structure everywhere. Instead, all models of general relativity with matter distributions show some sort of effects that we can consider, if you like, absolute velocity effects that distinguish one reference frame from all the others. And I'm specifically talking here at the beginning about uniform matter distributions, the cosmological models that best fit what we see in the sky, the Big Bang models, are idealized to have uniform distribution of matter in space. And in those models, the so-called cosmic rest frame has very interesting special properties compared to other rest frames which are in motion relative to it. There's a tendency, first of all, if you just shoot a bullet into one of these spacetimes, it doesn't just keep on going relative to the local rest frames at a constant velocity. It slows down and eventually comes to a halt. That's because of the expansion of space, really. But it's nevertheless an observable phenomenon. If you're riding that bullet, you can see your velocity relative to the local galaxy distribution slowing down and coming to a halt, which doesn't match the behavior of Minkowski spacetime at all. And then, even better, the inertial clocks run fastest when they are at rest relative to the average matter rest frame, which is a way of saying that the key factor that was supposed to make the twin paradox paradoxical in special relativity, which is that there's this symmetry, right? The people on Earth look at the astronauts' clocks and see them slow down, and the people on the rocket ship look at Earth clocks and see them slow down by exactly the same factor. That's gone. It's not the same factor, and in fact, the people on the rocket ship can look at our clocks and see that they're slowed down less, a lesser amount than what we see their clocks slowed down. And this is actually sufficient. You could be locked in a closet and not able to see the galaxy distribution, but as long as you know what the clocks of the various passing observers are doing, compare them by sending light signals, you can figure out who's at rest. So that's kind of interesting. At rest relative to the cosmic rest frame. Now, for me, this fact about general relativity and others that have to do with frame dragging and the way that inertia works give us hints towards a Machian origin, not just of inertia and the resistance to acceleration that we associate with inertia, but the space-time structure more generally, including the Minkowski local light cone type structure. In general relativity, gravity disappears as a force and gets folded into space-time structure, as we know. And often we focus on the inertial structure when we talk about this folding of gravity into space-time structure. And we emphasize that locally, the space-time still has a kind of a basically Minkowski space-time structure. We emphasize that to our students. And that makes you think that, really, still Minkowski spacetime is kind of the default, and all that general relativity does is, when you insert a bit of matter, sort of deform that default structure a little bit, but that doesn't change anything fundamental. And I think that's the way a lot of physicists think about it, but it doesn't have to be seen this way. So remember, Einstein's aim when he was working on general relativity was to implement the Machian idea that the distribution of matter entirely determines space-time structure. And for a while he thought he was doing it with his Einstein field equations, where little g is the metric, and and Einstein's tensor is a function of it. And this is the matter distribution given by the stress energy tensor. which is a function of physical fields and the metric again. Einstein's aim, which, as Julian mentioned yesterday, he articulated as sharply as he could in 1918, was not realized by the final theory, or at least not perfectly realized. Maybe it's not even totally conceptually coherent in the framework that Einstein laid out. But an intriguing fact is that the determination of inertial structure by the material distribution does seem to be achieved in precisely the realistic cosmic models, like the Big Bang models. Again, I was mentioning this before. The Big Bang models give us a kind of a preferred frame of reference in which the overall average matter distribution is at rest, and there's a correlative way of slicing space-time into space at a time. And again, this is observationally distinguishable. You don't even have to look at the cosmic microwave background, although it's even easier if you can do that. And that's why we know that our velocity with respect to this frame is something like 400 kilometers a second or something like that. Anyone can correct me if they know. So these facts about general relativity that I've been going over have led to some philosophers proposing to bring back a privileged frame and locate it in general relativity. Now, the proposals have included cosmic time that I just mentioned in the Big Bang models, which has to do with the average matter distribution. It's not well defined locally in realistic, inhomogeneous worlds like the one we live in. There's a further proposal that some philosophers have taken up, which looks for what's called the constant mean curvature reference frame. It's a little bit more technically defined than the cosmic rest frame, and it exists in many models. It's not clear whether it can be said to exist in our actual space-time. And then this is the idea that occurred to me when I was just working on this talk recently. Perhaps we can take that observational fact that I was highlighting and use it to come up with a new, more local criterion for a privileged reference frame, which would be the fastest inertial clock frame. Because we know that when there's matter in the distribution, all the reference frames moving relative to the matter, basically their clocks run slower compared to a certain privileged clock. So these are just ideas that one might pursue for saying, look, despite what we thought after seeing Einstein's special relativity, general relativity is not as hostile to the idea of making a privileged foliation of space-time as we might have thought. And that's really all I want to argue here. Now, this idea is criticized by Craig Callender in his recent book that I mentioned. His arguments are that our world is too complex and bumpy for this averaging strategy of the CMC or the cosmic frame to give us a unique frame. A second complaint that he makes is, why on earth should fundamental time, if it exists, march to that particular averaged scale? Averaging is a way of losing information about the world. Isn't it odd that something that purportedly metaphysically fundamental crucially hangs on information loss? And I think this is a reasonable complaint. The third one, he says, is the time functions defined are unique if you can get things to work out, but still the whiff of arbitrariness remains. Relativity, after all, doesn't distinguish the isotropic observers of Big Bang models in any as special in any way. Now, this latter complaint I want to say is actually tendentious. It's basically begging the question by taking the perspective we inherit from Minkowski spacetime, and which is the perspective usually taught to relativity students, and saying reference frames, indeed coordinate systems generally don't matter. And that's a perfectly legitimate perspective to take, but in the context of arguing with people who would like to find a preferred reference frame, it's a little bit question-begging. So I will move on because time's going fast, as it tends to do, and sum up that in general relativity, what I'd like you to believe is that we have an unclear situation for the possibility of temporal passage. As Callender says, the standard presentation of general relativity does not involve any privileging of any one way of slicing space-time, but nevertheless, there is a kind of a robust emergence of a preferred frame in any space-time where you really matter. And to me, the Machian aspects of general relativity give us a hint or point us to thinking about a framework in which coexistence may come back as something that's fundamental. Not in GR itself, but in future physics. So that's what I want to say about general relativity. Now, let's move to quantum theories, where I want to say that the verdict is again a bit unclear. You can think of passage as vindicated or destroyed, depending on how you want to spin things. Now, quantum mechanics allegedly brought indeterminism at the fundamental level of physics into play for the first time, and that was one of the big conceptual novelties of quantum mechanics. And to some philosophers like Karl Popper, that suggested the idea of an open future, that quantum mechanics was really endorsing this picture, which is common sense, of here's the present where things become fixed and the future is yet open because it's just not determined what will happen, but the past is fixed and beyond our control. And of course, this picture is assuming a shared now, right? This is now not a world line in Minkowski spacetime. This is the whole universe, right, in this picture. But the quantum measurement problem is the main conceptual issue with quantum mechanics, and Popper went on to suggest, and other philosophers have suggested, that maybe the way to resolve the quantum measurement problem is to believe in real collapses, and these collapses are actually what defines the edge of the fixed part of space-time and history from the open future. And this idea didn't hold much water, really. But let's talk about versions of quantum mechanics that do try to solve the measurement problem. And the interesting fact that I want to mention is that we basically have three ways of taking standard non-relativistic quantum mechanics as resolving the measurement problem, and all of them presuppose absolute time. First is just standard Copenhagen or orthodox 1930s presentation of quantum mechanics, where you really take seriously the idea of a collapse of the wave function on measurement. That was instantaneous, and the whole mathematical structure of the theory was basically set in Galilean spacetime, not in Minkowski spacetime. Bohmian mechanics is a different way of tackling the measurement problem. It's a different theory, of course, but it also is set in Galilean spacetime with an absolute time, and hence absolute simultaneity. And finally, the original Girardi-Rimini-Weber GRW spontaneous collapse theories were also, again, set in a context not of Minkowski spacetime, but of Galileo-Newtonian type space and time. Now, all of these theories, or all these approaches to quantum mechanics, tend to be rejected precisely because of their incompatibility with special relativity. And that's a fair complaint from a physics perspective. But it's still, it's interesting to me that trying to solve the measurement problem pushes you towards absolute simultaneity and absolute time. And if you want to solve the measurement problem without going that way, the only way I really know that plausibly can be argued to work is the Everett or many worlds interpretation, which is said to be compatible with special relativity. You can do either orthodox non-relativistic quantum mechanics or quantum field theories in the Everettian picture, and there's no absolute time is needed. Again, that's the claim. I'm not going to try to dispute that here, but it's a metaphysical picture that many are not willing to take very seriously. To end, then, I'm going to, let's see, I've been talking half an hour. I just want to say a little bit about the other really fascinating conceptual novelty of quantum mechanics and how that plays out with respect to time. And here, what I'm talking about are the EPR experiments done with entangled particles with spin. This is a schematic representation of measuring massive particles with spin, a pair of particles is emitted from a source and goes towards opposite sides of a laboratory where we have two Stern-Gerlach devices ready to measure spin of these particles. And the device, the analyzer or Stern-Gerlach, can be rotated to any angle we like along these axes. And then we either detect a given particle at one or the other, but not both. And the interesting thing about entangled particles in the singlet state is that if this is now, suppose our devices are oriented in the same direction, then what you find is that there's a perfect anti-correlation. So if the spin is measured to be up on the left side of the laboratory, it will be measured down on the right side of the laboratory. And that correlation is basically up to experimental error, it's perfect. And that's nice. That's in itself not that surprising. So this is what's illustrated here. I cribbed this from a famous Scientific American article by Despagnat. The more interesting stuff comes in when you consider that so there's this perfect correlation or anti-correlation when the devices are located, oriented in the same direction, but if you sort of rotate on one side compared to the other, there remains a correlation. It's not as strong, but it remains there until you rotate all the way to 90 degrees. And so if the orientation of the measuring devices is at right angles, there's basically no correlation or anti-correlation to be found. Now, John Bell, the genius of Bell in the 1960s was to think hard about this and prove a theorem that established limits on the upper boundaries on the correlation between these measurements at different angles if we assume that there's no non-local influence between the measurement on one side and that on the other. What do I mean by non-local influence? I mean somehow the result here is affected by, statistically, perhaps determined by, or perhaps simply statistically biased by, what happens over there, when what happens over there is space-like separated from my measurement here. Okay? That would be some sort of non-local influence. So Bell proved derived some inequalities giving the upper bound of the correlation at different angles, and pointed out that in fact quantum mechanics predicts stronger correlations than his limits, which is no surprise in a sense. You can do this, even undergraduates can do the calculation of what quantum mechanics predicts using standard non-relativistic quantum mechanics. But what's the surprise there? It's a non-local theory. It has these instantaneous collapses at a distance. Now, quantum mechanics' predictions have been repeatedly confirmed beyond question, and thus, the conclusion to draw, in my opinion, Bell's and many others, is that some sort of non-local influence has indeed been experimentally demonstrated, and this doesn't prove by any means, but it suggests that maybe what's going on is that there's a preferred frame. That in fact, one of the measurements happens first in reality and affects or determines, and that result affects or determines the result on the other side. How that works, nobody has a clear model for how that should work, nor can you figure out by any experimental means which one happens first, which one is the one that affects the other. That's totally impossible. And therefore, even though there may be influence between the measurements here and the space-like separated measurements there, we can't use that to communicate faster than light. We can't use it to send a signal. Now, interesting fact is that my description that I just gave, which I will defend in the question period if anyone wants to attack it, is rejected by almost all physicists that I've been interacting with in recent years. That wasn't true in the early years after Bell, but it is true today. And I'm not sure, it's a very strange sociological phenomenon that makes physicists want to deny with all the ferocity with which they're capable that there could be any sort of non-locality in nature. And we can talk about that. But what I assert is that Bell was right, and there is therefore a physical phenomenon which has been demonstrated in the laboratory, which involves some sort of influence or connection which is between events at space-like separated. Either that or backwards in time, or something even stranger, if you like. There are alternatives to some sort of influence, but they're even weirder. And again, what does this show us? It doesn't show us anything except it maybe can be taken as a hint that, that maybe there is a preferred frame after all, and that will help us make sense of how this works. So, this is just the stuff I was going through. The measurement results, and this is, I want to stress this, the measurement results from aspect experiments and others cannot be accounted for in terms of things in the causal past of the measurement events at each side of the laboratory. Nor can they be accounted for by pure random chance. And so the only alternatives to admitting a non-local causal influence are loony conspiracy theories. And some people pursue that, but it's not advisable. And again, apparently, and this is what David Wallace and others who advocate the Everett picture say, if you believe in Everett, you can get around this non-local influence. Now, I'm not sure I 100% believe that, but again, choose your poison. Even if they're right, is that what you would you really take the Everett pill rather than swallow a preferred frame in nature? So my non-conclusions, whether physics will turn out to be compatible with genuine coexistence, passage of time is still unclear. In both general relativity and quantum theory, there are intriguing intimations of re-emergence of a preferred frame, which is the precondition for temporal passage. And if you, like me, if you can't quite get your head around the idea of there not being temporal passage, then we can hope that some future quantum gravity theory will resolve the question, or at least make it less unclear. Maybe Chris will say things about that later. Thank you.
So there is one problem that's been known for a number of years with your suggestion that maybe the EPR correlations do show that we should have a preferred frame. And the problem is that if there's really absolutely no way to experimentally detect it with our very best and most sophisticated detectors, how could it be that that structure is what so centrally seems to govern our intuitions and our experiences as of a present and passage and becoming? That seems to be a severe disconnect, even if there is such an absolute preferred frame.
Yeah.
How would you bridge that gap?
I don't try to bridge that gap, and that takes me back to one of the things I said at the beginning, which is that I don't take us in our conscious experience to have any privileged access to the frame of becoming. We don't. I mean, I'm not a mind-body reductionist of a very strong sort, but I mean, I believe that physically, my seeing you now has to do with photons bouncing off you, going into my retina, and then stuff happening in my brain. And all of that story can be told in Minkowski spacetime, no problem. There's no, and it doesn't give me any access to anything beyond that in terms of spacetime structure. But it presupposes passage of time, and that's the conundrum. We can't tell that in a static block universe type picture, or so I would say.
I'll say a little bit more about constantly curvature variation. I just wanted to say, I think the really fundamental problem with Einstein's attempt to define Mach's principle, and it's actually, it shows how slowly conceptual ideas get recognized, is that Einstein didn't attribute mechanical degrees of freedom to the gravitational field. Once you recognize that the gravitational field has independent degrees of freedom, then they should be on an equal footing as regards Mach's principle with the matter. And it was 40 years from, it was in the 50s, that Hürtel and Dalen in Germany and Wheeler in Princeton first realized that you had to take that into account in the definition of math principle. And I will be saying something about that in my talk, but otherwise I'd like to talk very much.
Thank you. Yeah. I don't want to dispute that, yeah.
No, in fact, I wanted to ask something very similar to Chris's, and I mentioned that to you before. So you're rejecting any form of verificationism in your approach, because you're suggesting a preferred frame which is completely beyond our experience or ability to detect. And I wonder why, so what's the benefit of it? I mean, the drive to look for it is the fact that we take presentness very, very seriously because of our experience, because of the world pattern in our experience. Now you're offering kind of a present, let's call it, which our experience is blind to.
So I don't...
How does that address the...
No, the answer to that is that I'm not renouncing the necessity of some sort of contact with empirical experience and physical laboratory results and so forth. But I'm saying that has to come in the future. The fact that we can't now see how that would work is not a reason to reject the possibility that someday we will. And you know, any kind of verificationism of the sort that you can indict me with, I think, makes it also reprehensible to work on string theory today. But it's not. It's not reprehensible because there's the hope that as things develop and as these theories are improved, we'll find some way to make a connect with something that we can observe and confirm. So yeah, that's my perspective.
Yeah, of course, I like to talk very well organized. I have several problems with your talk, though. The first is the fact that the choice of the cosmic time frame is obviously modern dependent, because we have to assume homogeneity isotropy, and you have models, as you know, that cannot be treated in that way. Wherever you have closed loops, you don't have a cosmic time function. The second problem is that even if you have a cosmic time function, you don't have a previous one. It doesn't give you that. Maybe it's a necessary condition for the previous, but it doesn't. The third problem is it doesn't explain our experience at all.
All these things I agree with. And I wouldn't myself be an advocate of trying to save passage by appealing to the cosmic now, because I think that what you say and what Craig says in criticism is that, you know, an averaging procedure is a very bad way to think about something that's meant to be fundamental. Yeah. I agree. So all I was trying to say is that some philosophers have tried to use these as the wedge with which to reinsert some sort of privileged frame into general relativity as a necessary but by no means sufficient condition for finding the now in physics or relocating the now in physics.
I'm a physicist, and just to convince you that the fact that we have phenomena like the entanglement that we use daily, in accelerator we produce daily states which are correlated. And we use the fact that one is related to the other just to understand better the properties of these two states. But sometimes the reaction to elaboration on top of entanglement comes from the fact that people tend to ignore that quantum mechanics in general is an extremely powerful theory that we use daily, but we don't understand. So the problem is we don't understand why it works. It works perfectly, but we don't understand the uncertainty principle. We don't understand the exclusion Pauli principle. And we don't understand the entanglement. That means when this thing happens, we should be, we should wait. Maybe there is something hidden here and there that sooner or later we explain all this. But this is an attitude which is scientifically sound, an attitude that, on which scientists usually react. There is, okay, then we come to the conclusion. No? And then there is a new theory that explains all this. Because this is another bit of arrogance, I would say. Sometimes scientists are arrogant, but we should avoid being arrogant in contact.
So thanks. I agree with what you say. Although I'm one of those who would encourage scientists to keep being arrogant. I mean, I'm of a mind set that everything should be explainable, and so one day we should have a better understanding of the uncertainty principle and entanglement and all these things.
Coming up with this question of verification of a distinguished frame. In the talk yesterday from Eugenio, he showed Maxwell's equations, and he talked all about the ones that had the time derivative and the one upon C. He didn't say anything about the two equations which are purely involve spatial derivatives, that the divergence of the electric field is equal to the charge density, and the divergence of the magnetic field was vanished. Now these are actually elliptical equations, and you have to look at the whole of space-time to see that they're satisfied. In general relativity, you have such constraints which are infinitely more complicated, and do actually, there's quite a lot of strong evidence that they do distinct, there is a preferred frame, and that it is the constant mean curvature frame, which is very beautiful because it's analogous to soap bubbles in 3 dimensions. In four-dimensional space-time, it's analogous to soap bubbles in 3. So it looks very plausible. And you have to look at the whole universe in the simplest Machian model that Bruno Bertotti and I developed of just point particles in Euclidean space. The total angular momentum of the universe must be exactly 0. There's no way you can verify that except by verifying everything that's in the universe. And I think this could be exactly the same with the Bell inequalities.
Thanks.
And you need to check the whole universe in principle to do it.
That's good. I'll ask you for references where I can get up to speed on that thing. That's good, yeah.
Okay, so any other question?
Maybe one. I think you would agree with me that you can still explain why we share the now, even if, strictly speaking, from a physical point of view, the now is a point. There is a way to explain why we share now, even though, strictly speaking, my now and your now are different.
I would say it differently. I would say there is a way of explaining why it feels to us like we share a now, even if we don't. Taking these pointy nows that you're talking about.
Isn't that enough? I mean, light is no speed, and things don't change too much around.
So my interest in finding room for temporal passage is not in order to explain experience. I tell the cognitive science story in Minkowski space-time. You won't run into any trouble. I mean, because we have no preferred frame goggles in our minds. That's not how it works. So yeah.
research interests in quantum gravity and the history of science. His 1999 book, The End of Time, advances timeless physics. The controversial view that time, as we perceive it, does not exist as anything other than an illusion, and that a number of problems in physical theories arise from assuming that it doesn't exist. Barbour's theory goes farther in skepticism than the block universe theory, since it denies not only the passage of time, but the existence of an external dimension of time. In the last few years, he has explored, together with several students, the implication of the relativity of size. The previous perspective is reflected in a theory of gravity that Barbour shaped and produced. It retains the essential dimension of general relativity while removing, in a well-motivated way, structure that is potentially redundant and may be well responsible for the difficulties in the creation of quantum gravity.
Thank you very much. I hope you can hear me at the back all right. I was once an officer in the British Army, so you don't have to speak very loudly. Only military service, not as a professional. Most of my talk is going to be about the problem of the arrow of time, but I will start with saying a little bit about these problems of whether there's a universal now. I'd just like to show a list of here my collaborators and a few papers. And I do recommend those who want to follow this up, this book that came out just over a year ago by my collaborator Flavio McCarthy, Shape Dynamics. It's a very nice account of the whole story, historical background going back to the Newton-Leibniz debate about absolute or relative motion. It's a very nice account of the work that I did with Bruno Bertotti. So I strongly recommend that, Carl in particular, if you want to catch up with things there. Now, I'll just say something about instants of time, how I conceive them, and also very important, there's two notions of relativity which need to be distinguished and got completely muddled up because of the way Einstein created general relativity. Okay, that seems to be there. So, Mach originally, when Mach talked about relativity of motion, he meant how bodies move relative to each other. He still believed in absolute time at that stage. So, motion is relative to other bodies in the universe. That's the meaning of relativity in Mach's terms. But in Einstein's term, once Minkowski had introduced the notion of space-time, it was how you slice space-time. That's a completely different notion of relativity, and that has to be clearly distinguished when you're talking about it. And it's my belief, actually, that it's the Machian one that is more fundamental and gives you a deeper insight into the structure of general relativity. And so my notion of an instant of time, and it is compatible with Einsteinian relativity, is it's not so much the distances between the particles, but the ratios of the distances, that it's the shape of the universe in one instant. So if we take the simplest non-trivial model universe we could have, it would be the Newtonian three-body problem, where at any instant the three particles form a triangle, which has a shape and a size. And shape dynamics is saying the only physically meaningful thing is the shape, because the shape is defined by the internal angles. They are dimensionless, they're pure numbers, they are ratios of lengths. So it's saying that the only things that are physically meaningful are ratios. And that has an incredibly far-reaching consequences, I hope, as I shall persuade you. I think it has the potential to completely solve once and for all the problem of irreversibility and the arrows of time. So that's what my talk is going to be about. So the problem of time reversal symmetry is that the laws of nature distinguish no direction of time. You can reverse the velocities. If you take a film of two billiard balls colliding and run it backwards, you can't tell the difference. However, somebody dives into the swimming pool and you run that backwards, it's blindingly obvious something has gone wrong. So the question is, where does the arrow of time come from? And this was the problem that Boltzmann in the 1890s in a famous debate with Sermolo confronted, and he failed to resolve it, but it had been raised earlier in 1852 in a paper by Lord Kelvin, or William Thomson as he then was, who said there is a universal tendency in nature to the dissipation of mechanical energy. And that, by the way, that paper then became very important in the debate between people who believed in evolution and geology that had taken over a long time, and Lord Kelvin. That's a very interesting story in its own right. So that's the problem. Now, I'm going to suggest that the problem came because people didn't realize where thermodynamics came from. Thermodynamics arose from the most wonderful book, it's one of the most wonderful books in the history of science, Sadi Carnot's book, Reflections on the Motive Power of Heat, published in 1824. And what he set out to do was to say, how can you make a steam engine work with the maximum efficiency which is possible? And the key thing in a steam engine is the steam has to be confined in a cylinder because of the continuous operation of the steam engine. Once it's done one movement of the cylinder, you have to bring it back again to get the working medium in exactly the same state as it was before. It's a continuous process. This is what's going on in the Carnot cycle. And that meant that it had to be in a cylinder or in a box. And I would say it is quite staggering in thousands of papers and discussions of the problem of the arrow of time. This simple fact of the origin of thermodynamics came out of the study of the steam engine has not been recognized as far as I can see. And I'll show you what are the consequences of that. If you have a box, because of the box, if you have a non-equilibrium state, it will equilibrate essentially because the particles bounce off each other elastically. But vastly important, they bounce off the walls of the box elastically, and they cannot escape from the box. So they're bound eventually, almost with huge probability, to settle down very soon to essentially an equilibrium uniform distribution. And Maxwell showed how the velocities could be distributed, and Boltzmann's task for 3 or 4 decades was to show how the Maxwell distribution gets established if you start off without a Maxwell distribution. And so you can do everything once you've got things in a box. And that mentality has maintained, has stayed to this day when people talk about it. So what are the consequences of a confining box? You have something which is called Poincare recurrence. Now, Poincare recurrence is very important. Poincare proved a theorem which is, it relies on 2 things. First of all, it's basically a dynamical system. It can be a very general one, particularly given often is when it's a Hamiltonian theory. But absolutely critical, the system only has access to a phase space of bounded volume. It's a compact phase space. So as far as space, it's actually the system can't occupy infinite space. It must be confined in a box. And also the velocities can't grow, the momentum can't grow without bounds. And then you combine something called Liouville's theorem. Now Liouville's theorem is basically, you can think of it, if you put a patch of oil in a stream which is flowing in different ways, you can show, if it's a Hamiltonian flow, that the area of the patch of oil remains constant. That's the way to think about Liouville's theorem. And Poincare's recurrence theorem starts with assuming Liouville's theorem, and then in addition makes the additional assumption that the phase space is compact. And that is what causes the Poincare recurrence theorem. And that is what then leads to the fact that essentially inside that box, if you watch for the great lengths of time, you have heat death where there's perfect thermal, near perfect thermal equilibrium, and then every now and then you will get deep dips of the entropy, but they're immensely far apart. And Boltzmann in 1895 said he assumed that the universe is and rests forever in thermal equilibrium. Only near the deep entropy dips are worlds where visible motion and life exist. The direction of time towards the more improbable state will be experienced as the past. So if we have here intelligent beings near a big dip, this is where there's low entropy, and these people here will say that's the direction to the past, and these ones will say that's the direction to the past. So you have opposite pointing arrows of time, and Boltzmann said the direction of time is determined by the direction of increasing entropy. Now I'm going to propose something a bit similar, but it's going to be still very fundamentally different, because it's taking away this assumption of Boltzmann which is that the universe is and rests forever in thermal equilibrium. That presupposes the universe is in a box. In the 19th century, when thermodynamics was developed, none of these people had the remotest idea about what the universe was like. But the universe was discovered to be expanding in the 1920s and 30s. And I don't think anybody's taken this on board since then. If you read, for example, Roger Penrose's books, it's quite clear that implicitly he believes that we're still in a situation where Poincaré recurrence holds. But does Poincaré recurrence hold in an expanding universe? The simple answer is it cannot. The Poincaré recurrence does not. The Liouville theorem holds in an expanding universe, but the Poincaré recurrence does not. And I think this is just the simple explanation of why people go into a model. I'm not saying I'm right, but I think we've got a good chance. So let me drink a bit of water. So I'm now going to introduce the idea of a Janus point system. I'm going to conjecture that you should think not so much of local laws of nature, but of laws of the universe. I'm going to suggest that there is a dynamical law, that the universe is governed by dynamical laws, but it is such that every single solution of that law divides into two equal halves at more or less qualitatively simple halves at a unique Janus point, named after the Roman god, obviously. The evolution is time asymmetric either side, but overall there is perfect symmetry underlying the time reversal symmetry of the law. And arrows of time, experienced time, point in opposite directions away from the Janus point. This is very like Boltzmann, but the explanation for it is totally different. It's nothing to do with a statistical fluctuation. And the hypothesis, as I say, the hypothesis is that the law of the universe dictates a Janus point in all of its solutions. And now I'm going to give you an example where that happens. This is the first qualitative result discovered in dynamics by Lagrange in 1772, studying the three-body problem. There is a quantity, let's not get into all of the mathematics too much. There is either, you can call it the center of mass, moment of inertia, and its square root is the root mean square length. So the root mean square length is basically something which measures the size of the system. For those of you sitting here, your root mean square length is basically, it takes into account your masses, but you've all got about the same mass. It's basically the diameter of the seats in which you're sitting. It's about 10 meters for you sitting there. So that's the root mean square length of your system. And what Lagrange found was that if you consider the three-body problem, for which the energy is either exactly zero or positive, that root mean square length, measuring the sizes of the system, if you plot it as a function of time, is U-shaped upwards. It goes from plus infinity down to a minimum value, that's my Janus point, and back up again. And that is a very simple, you can prove that, that's a two-line proof to prove that. And it holds not only for the three-body problem, but for the n-body problem. This is the qualitative result. Now, so far as I know, this result is extremely well known to people who work in the n-body problem as a mathematical problem. I don't think it's known to anybody except Poincaré. Well, Poincaré must have known it. But I don't think it's known to any of the people who've been interested in the problem of the arrow of time. And I don't think Boltzmann knew about it. Equally, the people who study the n-body problem are not interested in the problem of the arrow of time. I know that because I've interacted with some of the best n-body specialists in the world. So I think this may be an extraordinary state of affairs. But there it is. So and even if you have negative energy, basically the system will break up in time. You won't have a unique Janus point, but you'll have a finite number of them. So this completely changes the situation. And in such a situation, you cannot have Poincaré recurrence. It never goes back remotely anywhere near the state it was before. It just can't happen. So now I'm going to come back and say the only things that can really count are shapes. So let's just think about, and the wonderful thing if you have the three-body problem is you can talk about shapes of the system, because the triangle, the shape of the triangle is defined by two internal angles. So basically you can represent them by latitude and longitude on the surface of a sphere. So what is this picture here? So The equator is all those limiting cases of triangles where the three particles are exactly on a line. That is technically still a triangle. Okay, so the equator is there. Each point on the sphere represents the shape of a triangle by means of latitude and longitude. So it's representing the two internal angles in a certain way. This is plotted for equal masses. So the points in the northern hemisphere that have the same longitude, but the points that have the same longitude but opposite latitude are mirror images of each other. Those are the two incongruent stars. So you pass from the mirror image from one side to the other as you pass through there. The three-body problem with zero angular momentum, by the way, always plays out in a plane. So those are the things that I'll explain the color coding in a moment there. So then there are 6 special, so first of all the equilateral triangles are very special. They are at the poles. There are the collinear configurations, they're called Euler configurations. And then there are 3 more points where 2 particles are infinitely close to each other compared with the distance to the third. The ratio of this length to that length becomes 0. That's what this point means here. So that's the shape space there. And it's a beautiful way there. Now you can, if I were to ask, is there some quantity whereby I can characterize how much you, as you sit there, are clustered in people sitting together close to each other or uniformly spread out, that does not depend upon my unit of distance and is just, so to speak, a measure of, it doesn't depend upon the scale, it's a scale invariant quantity that measures how much you're clustered by. It turns out this is an extraordinarily interesting quantity, which probably is very fundamentally significant in mathematics. It does that wonderfully, beautifully. And so basically here I see, looking at you, there are sort of quite a lot of you where 2 people are sitting quite close to each other. There's 2 females of the human species there. I see smiling at me very close to each other. And I think one is called Anna, if my memory serves me right, from last night. But of course there's quite a big gap there. So in some sense there's quite a lot of clustering in you. So basically there are 2 quantities which have the dimensions of length. One is the one that I've already mentioned, which is the root mean square length. You take the sum of this, you take the squares of all the distances between the pairs of objects, you add up all the squares, you multiply by the corresponding masses, and then you take the square root. And don't bother about the total mass, that's just there to sort out, but there's no dimension dependent on that. And then there's what's called the mean harmonic length, and the mean harmonic length is essentially the inverse of the Newton potential. These are 2 very fundamental quantities there. And if you take their ratio, that gives you a dimensionless quantity. It is a pure number. And it characterizes very sensitively how clustered a system is. And the reason is that the root mean square length, if you have a lot of people, changes very little if 2 people get together. If Anna and the person she's sitting next to move a few inches close to each other, that does virtually nothing to the root mean square length of this room. However, it will change the gravitational potential energy quite significantly if they move closer to each other. So that's a very significant factor. And for that reason, this is a very sensitive measure of clustering. And the interesting thing also is that it's the negative of what the n-body people call the shape potential. Now the Newton potential does 2 things. It pulls all objects towards the common centre of mass, changing the size without changing the shape. Those are one lot of forces that come out of the Newton potential. Those are invisible for people living within the universe because they can only see ratios. There is other things which change the shape of the universe, and those are things that are visible within the universe, and those are governed by the shape potential. So this quantity measures how clustered the universe is, and simultaneously it's the one that generates the forces that change the shape of the universe. So we're talking about the very foundations of the theory. And here's two shapes here. This is a sort of a glass. This is what glassy distributions in glasses, what the molecules in glasses look like that. Very uniform distribution. This is a Poisson distribution. You see they look very different to the eye, and that quantity there that I defined there, the complexity, it distinguishes very well. You put in and work out the numbers for these two distributions, you find that this is clearly larger than that one. This is lower. This is more uniform. So let me go on. Now, how am I doing for time?
Still at 15 minutes or more.
15 minutes or more. Now, for about 100 years, it's been known what every single solution of the Newtonian three-body problem with zero energy and zero angular momentum looks like. It's extremely interesting, and for me, it's the model of the explanation of the arrows of time. So basically, in the very distant past, this plays out in a plane because the vanishing angular momentum means it's all in the plane. So in the very distant past, you have a single particle which is moving inertially towards two particles going around each other. This is what we call a Kepler pair because they're orbiting their common center of mass in a Keplerian ellipsis. And out here, gravity only affects essentially the Kepler pair. It's the singleton over here has a minimal effect. But when they get closer to each other, three-body interactions become important. The motion becomes chaotic. It's not at all easy to predict what will happen. In this case, there is a swapping of partners. And the singleton pairs up with the green part of the Kepler pair, and they go off and form a Kepler pair going down here, and the singleton goes off that way there. And that's, but these arrows indicate purely nominally the direction of motion and the direction of time, because if this is the whole universe, it's completely nominal. You can just reverse the arrows, and the only difference is you have qualitatively the same story. It's only the question of whether the Kepler pair is more tightly bound at the start of the story or more loosely bound at the start of the story. There is no way of distinguishing between the two. In the real universe, if you have three particles interacting with each other, the background universe defines the direction of time, and you tie yourself into the background direction of time defined by the universe. But that's what it looks like there. That's the conventional story, and the problem of the direction of time seems insoluble in that. But let's look at it in a different way, and this is where we get like Boltzmann, but without Poincare recurrence. Now let us look at it. Let's look how the shape of the triangle changes in this motion. This triangle here corresponds to when the singleton is there and the Kepler pair is very far away. The next one is when they go closer to each other. And this is when they're near the interaction, when the shapes run through basically all shapes of the triangle in principle and might get very close to the equilateral triangle at the Janus point. This is the Janus point just up there. But out there, you get more and more like needles or shards is there. But now, let us now think about this in a quite different way. Let us say that this, so if I was to take my grandson of nearly 5 to say, can you assign directions of time here objectively using just the shape of the universe? He'll say, well, there's two, Grandpa. They point away from the equilateral triangle in opposite directions. That's blindingly obvious. You cannot fail to see that. I think you'll agree with that. Okay, so there's two oppositely, but these are my Janus point. These are two my arrows. This is the Janus point here. So they're points away from that. And moreover, it's extremely interesting. You have something happening which is not remotely like what happens in a box of atoms in a box. You get the growth of structure in a most marvelous way, because as you come out, here it's chaotic. You don't have anything that looks sensible. But as you get further away, the Kepler pair becomes a clock, it becomes a rod through the length of its semi-major axis, and it becomes a compass. It points in a direction. So the Kepler pair becomes three things all at once, with ever better accuracy. And with respect to that rod, clock, and compass, you can verify that the singleton is moving inertially and is obeying Newton's first law. That is all emergent, out of chaos. All that emerges out of chaos. And this is totally unlike what happens when you come out from a dip in a box, because then you go from order to chaos. And you don't get anything remotely like that. and not even if you go backwards. So this is entirely due to the fact that you're in a completely different situation. And this is what it looks like in here. That's that same thing here. So what you can't see, this is the root mean square length, or the moment of inertia. This is its first derivative. These are not visible directly to observers within the universe. This is what you can see. These are the fluctuations in the complexity. And the fluctuations, which are superimposed on a general growth, comes about because the Kepler pairs are formed with eccentricity. So the two particles in the Kepler pair have different fluctuating distances. That's what's causing these fluctuations. This is what is observable there. So, and the age of metrology dawns when these orbital elements stabilize. As soon as you get away from there, you can talk about rods, clocks, and measurements and numbers, and we're in the familiar world where we exist at the moment. And this is what happens with a 1,000-body simulation. Those fluctuations get smoothed out. This is an artistic impression of what it's like. It's almost certain, high probability you will have a very symmetric thing. Here, at the Janus point, it looks like thermal equilibrium. At that point there, it's like a swarm of bees all moving in random directions. So this is where you have thermal equilibrium. And out here, you get clusters forming. You have rods and clocks. You can measure things. And all of these Kepler pairs, they march in step with each other. I was talking about clocks that march in step with each other. And the angles between their major axes stay constant. It's the most extraordinary creation of order out of chaos. And when Newton looked at the solar system, he had this wonderful thing. It is not to be conceived that mere mechanical causes could give birth to so many regular motions. This most beautiful system of the sun, planets and comets could only proceed from the counsel and dominion of an intelligent and powerful being. Newton just didn't realize how powerful his law was. It all comes out of the Newtonian n-body problem. Creation of order out of chaos. And the story, it's not a clockwork universe, it's a very incredibly rich story which unfolds in two opposite directions away from the Janus point. I'm getting near the end, I think. So this is the story according to NASA. This is meant to be the Big Bang with quantum fluctuations. And it's said that entropy increases as in the universe. The entropy of the universe increases. That's what Clausius said. Didn't look to me remotely like entropy increasing when I showed you the previous slide. And this doesn't look to me like entropy increasing. Beautiful order. Here's the W-map thing that did those wonderful experiments measuring all the fluctuations from the microwave background. Looks like fantastic order to me. Where's the disorder here? Look, can anybody tell me where the disorder is? I don't think it's there. I think it's a figment of our imagination. So I think, so this is what Lord Kelvin said in 1852. I would say the universe is a universal tendency of the universe to create structure. I think that's the story of the universe. You got it quite wrong? So this is really what it should look like, the universe. By the way, this is all classical. We're not yet getting to grips with any of the problems of quantum mechanics. So the origin of the second law. The second law holds when you've got systems which are literally confined in a box, or they're self-confined, like galaxies are self-confined by their gravitational potential. And in this case, what happens here is that subsystems of the universe form, and they are self-confined. And then at this stage, the ordinary second law of thermodynamics comes into play because you've got systems which are essentially in a box. So from now on, within these systems, the conventional second law of thermodynamics does apply. But overall, we can define an entropy-like quantity for the universe, but the entropy-like quantity for the universe decreases. This corresponds to the fact that subsystems are forming, and then within those subsystems, the ordinary second law of thermodynamics comes into play. So that's how we change things around completely. So what I would say is the law of the universe creates conditions for all steam engines to exist. Man discovers entropy by maximizing their efficiency. I couldn't resist a quotation from Shakespeare's sonnet, and nothing against time's scythe can make defense, save breed to braver when he takes thee hence. I'm not saying this is necessarily an optimistic future for the universe. It might, I don't think it'll look like thermal equilibrium. Or it may, I don't know, I don't mind about that. I think it might look like an extremely beautiful graveyard with beautifully engraved gravestones. But I'll leave you that one there. Leibniz said we live in the best possible of all, we live in the best of all possible worlds. When you look at his monadology, he says we live in the most varied of all possible worlds. Subject being created by the simplest possible rules. And maybe he could modify Leibniz's idea to say that it's not eternally perfect, but it's striving to become more perfect. So to perfection. And so maybe infinite information at the Janus point is unfolded as perfection in the fullness of time. And I'll finish with just this one slide here. Is in fact structure and beauty created by law through time, from the Janus point in two opposite directions. So that gives us a little time for questions. Thank you.
Thank you. So thank you very much. If I understood correctly, nothing in your entire argument depended on the fundamental laws being quantum. This was purely classical. So I'm wondering about your thoughts, how maybe turning them into quantum laws would change any of the story, or why not?
We are hopeful that we can, one of my collaborators, Tim Kozlowski, very likes Bohmian mechanics and thinks that he can make a quantum theory of the universe in which Bohmian mechanics basically have the same Janus point idea. My own idea is that it's very interesting that Everett talked about the branching of the wave function, and somebody, I think it may have been Bryce DeWitt, said it only branches into the future, not to the past. There's comments from on documents that were left behind by Everett, where that comment was made. He wrote at the margin bullshit. That he believed that because of time reversal symmetry, there must be branching in both directions. But I think there's quite a good argument that by Liouville's theorem, there will be branching only forwards, so that one will resolve the problem of whether there is symmetric, time reversal symmetric branching forwards and backwards. And you can actually see something like that already happening in the three-body. I don't know whether it'll go back quickly. Yes, it does go back nice and quickly, thank you. It's working well, that's warmed up. If you, I haven't got the trajectories of the three-body problem on this, when you apply Liouville's theorem says the phase space volume must remain constant. If the system can expand, then if you have a Gibbs ensemble and the size part grows, to conserve the volume, the shape paths must contract. And that means there are attractors on shape space. So wherever the Janus point is here, you will find the trajectory of the system. It will always finish up, it always goes to there. So it's bound to go there. Now, how does the chaos in the three-body problem reflect itself in this picture? It reflects that if you're near the Janus point and you slightly change the elements, the data, it's very hard to predict which of these things the system will finish up in. It flips. It will flip over there. That's what chaos plays out in this picture there. So if you now form suppose we have a Janus point here, and we have a whole collection of particles of classical trajectories making a Gibbs ensemble, which start off all going together. They will split up, some will go down one, some will go down others. And that's very like what happens with splitting of a wave function left to itself, I think. So I'm a bit hopeful we might add strength to the many worlds interpretation. My own, David Deutsch, I describe David Deutsch and David Wallace as messianic believers in the many worlds interpretation, and myself as an apologetic believer in it. I think it's very hard to dismiss many worlds out of hand. I mean, I don't deny there aren't all sorts of problems, but I think it's very difficult to dismiss it out of hand.
The weak interactions are very important components of our universe.
Yeah.
And they are not symmetrically timed. So your statement that the laws of physics of nature are symmetric time is wrong.
With respect, CPT is timed is reversal. Already it's long been recognized, long before CPT came up, that if you have particles, charged particles in a magnetic field, time reversal involves not only reversal of the momentum of the particles, but also the reversal of the magnetic field. So I just take that to be just another case, just a bit more sophisticated example of that.
But we cannot state this because many people, particularly people that are not physicists, they continue to say that the laws of nature, if you change time, are the same. It's not true. It's simply not true.
No, I'm saying the reversal, the reversal under a symmetry operation is more sophisticated than just reversal of the direction of motion. It involves changing particles into antiparticles and a mirror reflection.
P and T.
Yeah.
So we can say they are symmetric. We can say that the laws of nature are symmetric under change, the symmetry of charge, parity, and time.
Yeah.
If you isolate time, it's simply wrong.
No, I agree. I'm not disagreeing with you. But let me tell you something which is very interesting. If you take, how familiar are you with, in general relativity, the simplest non-trivial model of general relativity, vacuum gravity with a massless scalar field gives you what's called quiescent Bianchi line. Now, quiescent Bianchi line is very like the Newtonian three-body problem, but it's very interesting. The Janus point in the three-body problem can be anywhere on the shape sphere. There's a shape sphere of the Bianchi 9, and the shape sphere of the Bianchi 9 must be on the equator. And on the equator, not only does the direction of time flip, but also the spatial orientation. So you've got T and P changing. And we think it's entirely possible that charge conjugation. So on the analog of the Newtonian three-body problem, in Bianchi 9, quiescent Bianchi 9, you could well have CPT. And there is something called the BKL conjecture, Bilavin, Kalatnikov, and Lifshitz conjecture about what happens at the Big Bang if it's quiescent, where there's a massless scalar field or a stiff fluid, and we think it's entirely possible that you get CPT happening there. So I think this is potentially very interesting, but you're quite right to make, thank you for making the observation.
Yes, as far as I can understand, it's a great talk, thanks, Julian, but I want to understand what this theory is about. First of all, you seem to be inclined to accept many worlds interpretation of theory, but that's about the wave function. And the wave function lives in the free-end configuration space. On the other hand, here you seem to assume a particle ontology. And so what is your choice here? And what about photons? Where is...
Thank you. That was very good. I was qualified thing. My justification is the following. One of the really great discoveries in the history of science was the discovery of entropy and its interpretation by Boltzmann as a count of microstates. You define a state function and then you look at all the microstates that are compatible with that. And all that was done with the simplest conceivable model you like to make of the universe or a system in a box. Elastic spheres or an ideal gas. And I would say that our model is at that same level. But if we can explain how something like entropy arises and we can look like we've got the basis of a solution to the problem of the arrow of time with the simplest conceivable model, analogous to the one which led to this fantastic development of statistical mechanics from the 1850s onwards, I think we may be in business. So this is, if we're on the right track, it will be a long lot of research before it's verified that this is the real resolution to the thing. And I keep an open mind about quantum mechanics and quantum gravity and things like that. I think my aim at the moment is to get people to think out of the box. I've looked at a lot of the literature on the arrow of time. I have not once seen a single person ask whether that box is an important fact. If you read Richard Feynman's lectures on physics, he gives an account 30 years after the expansion of the universe was discovered, when he clearly is still thinking the universe is in the box. Completely ignorant. Although with Feynman, with Wheeler, he tried to develop a theory to explain retarded evolution to do with the expansion of the universe. He's still completely ignoring that. He's just thinking like Boltzmann did in the 1890s. Roger Penrose, if you look at everywhere where Roger Penrose talks about it, it's clearly, he's unaware of the fact that he's implicitly assuming the Poincare recurrent code. He's just unaware of that fact. And I think it just goes for everybody who writes on the subject. I think it's just the extraordinary state of affairs. It's a case of the child saying the emperor's got no clothes on. He's not in a box. He's naked, and that changes things utterly.
Just ask, are you familiar with the recent proposal by Neil Turok and the other guys in Canada about a CTP symmetric universe? I think it matches quite significantly with your nice discussion. Essentially, it's not quite familiar myself enough because it's really very recent, but they propose essentially symmetry, original symmetry between matter and antimatter with the flow of time that goes reverse in the two parts of the universe. I don't know if you have it appeared in the Physical Review letters a couple of weeks ago.
I missed that. I'm afraid I'm so busy writing a book about this that I'm not following the literature. I am a bit aware of that. I have visited Perimeter quite a lot. In fact, Neil Turok, I spoke about this, and Neil was actually very interested. I think partly because it was like I did. I'm not sure, are they assuming exact symmetry, that the two halves are exactly the same, or are they qualitatively the same?
I think they are qualitatively the same.
Yeah, well that would be very like ours. I mean, maybe we have, I don't know what the basis of their thing is, maybe they're just postulating it, but in our case, it comes straight out of the dynamical law. And by the way, I mean, we originally had this idea I got the idea from Lagrange's result, and then after we'd been working and developing that from it, we suddenly said, hang on, can we get it in general relativity? And if you've got just vacuum gravity, it doesn't work. The curve goes on, you never get to a Janus point in vacuum gravity in the Yankee 9 model. It goes on forever. And we didn't know, the three of us who were originally working together, and then David Sloan, who was very good, he did know about quiescent Yankee 9, and then lo and behold, in quiescent Yankee 9, you can get through. So this is very interesting. So now we think this could really change the way you think about singularities in general relativity. The Hawking-Penrose theorems are clearly correct, but they only refer to the scale of the universe, when the universe size goes to zero. But what we're saying is that actually, if you only look at the shape, you can go through the Big Bang. The shape degrees of freedom go through smoothly. At least I'm relying on their mathematics. I've talked about the analogous problem in the three-body problem with the n-body specialists in Paris with whom I interact. They think it could be okay, but I think that really needs to be firmed up mathematically to see that. But that would then say that the Hawking-Penrose theorems are mathematically correct, but they've been given quite the wrong physical interpretation. That would be our position there. And this might change things, who knows. I mean, this is very early stages yet. We're a small group, essentially there's 4 of us working on this. The other 3 are tremendously busy with other things. 2 of them are desperately trying to get jobs, which is the purgatory in which postdocs live. You know, they get a postdoc position and they've been in it 3 months and they're already making applications for the next one. Instead of doing something interesting research, which is why I was independent, to avoid that problem.
Yes. Hi, thank you so much for this interesting talk. I have a question about a term that is very important for the philosopher that study time. I have this question. In this theory, are there any place and meaning of the phenomenon like memory, like the series and the entertainment of past?
Now, in my book, The End of Time, I introduced the notion of a time capsule. By time capsule, I don't mean something that builders put into a house with coins and things and newspapers from the time the house was built. I mean a static structure, an unchanging static structure, which when you look at it and you look at all the evidence, you say this contains mutually consistent records, which tells you that this one static structure has come about through physical laws acting through a great length of time from a certain initial condition, has created this static structure. This was the conclusion geologists came to towards the end of the 18th century, looking at the surface of the Earth. And there's an absolutely wonderful comment I came across recently by Lamarck, who was one of the people very interested in this question of geology. He said that the surface of the Earth is its own historian. Fabulous comment, in my opinion. So it's all, and I also in my book, The End of Time, I have the comment, time is, the instant is not in time, time is in the instant. How can I stand here and say, I remember my childhood? It's because of all the consistent memories I can call up in my own, and I live, in terms of what I can observe and know, I live an entirely solipsistic existence. I'm not a solipsist, I certainly believe you guys are here. But as far as I have access to any evidence, I'm totally on my own. I have nothing else. I mean, very often, when I'm giving a talk, I mean, you saw it actually this evening, just to make sure that my memory is reliable, I check that she is called Anna, and she smiled back. There's the consistency of the evidence. This is why you can, this is what science is about. It's connecting all the evidence that you can find and seeing that it makes a consistent story. And you've always smiled to me too, because he didn't like this, what science is doing, did you, Bob? But I'm taking my revenge on you, just gently. And you're smiling, you say, that's the sort of thing, and this is all in my head. For God's sake, it's in my head, my consciousness. And it's that consistency. There's a wonderful line at the end of Shakespeare, near the end of Shakespeare's Midsummer Night's Dream, where Theseus and Hippolyta have come across the lovers, and they're telling this incredible story of what they experienced in the night. And Theseus said, oh, these are, you know, the madmen, the lovers, and the lunatics are all the same, you know, their brains just run too fast, you know, they're manic and so forth. And Hippolyta says, yes, but it all hangs together. You know, the facts fit together from which, you know, pick up what each of them said, and you know, it grows to a thing of great consistency, she says. That's for me one of the great lines in Shakespeare. And that's what's going on in my head here. I mean, how do you pronounce it? Is it Aquila or Aquila? L'Aquila. Yeah, L'Aquila, yes, but I wondered if you dropped the L, whether it's...
No, we do not.
We do not, it's always L'Aquila, yes, thank you, yes. You know, so it all fits together. You know, I met Carl came to on the conference we had in Tübingen in 1993 on Marx principles. and things like that. That's the basis for the past, and believing in that there was history and so forth. It's all very consistent. Hippolytus, right? He rose to a thing of great consistency.
Any other questions? So that 30 minutes break and
c'è una proprio di qualità, esami psicologici, costa un po' però. C'è un altro modello? Sì.
Hi, Matthew. Good morning. How are you? Right on. Experiencing another short time.
What's that?
Are you just right?
No,
Because I was going around.
Non è facile, perché all'ultimo momento fare tra l'uno e l'altro. È quello che facevo anch'io. E poi le slide in italiano.
Maybe. What time is it? Okay. We should wait till. We'll wait. Because.
Sto zio è nato ancora là. Ma possiamo mettere il microfono là? Così. Questo microfono ci sta facendo impazzire. Che si sente il rimbombo del microfono, non zio. Non lo deve andare a posto? No, non è microfonia.
No, questo capta solo, non rimanda.
Ah.
Lo usa la camera.
Ah, ok, allora. Sì, adesso lo sento.
Che telefonino qualcosa.
Io non lo sento. Ok, ma comunque lei è sicuramente più esperto di noi di queste cose.
Ci provo. Però lo sentivo, si sentiva proprio dall'altoparlante.
Sì, ma da tutti gli altri.
Sì.
Infatti io pensavo che era un piano di microfonia che rimomba, si può dire.
Però questo non fa parte di piano, cioè non devo prendere l'aula, non abbiamo uscita, non dobbiamo.
Yes, we can start, and I'm glad to present Christian Wüttrich, who is a philosopher, associate professor at the University of Geneva. His primary research focus is in the philosophical foundations of quantum gravity, but he works also in philosophy of physics, philosophy of science, and metaphysics. Specifically, he works on space and time, time travel, persistence, identity, laws of nature, determinism, and causation. He also has interest in philosophy of mathematics, epistemology, and philosophy of mind. From September 2015 to August 2018, he is running a large project called Space and Time After Quantum Gravity, funded by the John Templeton Foundation of Howard, of its two centers at Chicago and Geneva. The joint activities for this project are chronicled in his blog Beyond Space-Time. And I'd like to suggest you two forthcoming books. The first one, together with Nick Haggett, title is Out of Nowhere, The Emergence of Space-Time in Quantum Theories of Gravity. And the other one, together with John J.B. Manchak and Chris Menck, Time and Again, on the logical, metaphysical, and physical possibility of time travel. I'll give you the floor. Welcome.
Thank you very much. I'd rather not use the microphone and just yell. I have not been an officer in the Swiss Army, but I have two kids, so I'm used to yelling. Anyway, let me start by thanking the organizers for their very kind invitation, which I'm honored and pleased to have accepted, of course, to come here and talk. And I should say that I would like to dedicate this talk to the people of Latvia who have suffered 10 years ago tonight from a calamitous earthquake, from which we still recovering. And I'm very happy to contribute, however tiny and insignificant contribution I can make to the rebirth of Latvia. So may the eagle rise again. Okay. In my title, I seem to give three options. 2 times, 1 time, no time at all. I'm going to explain each one of these parts in the course of my talk. It's somewhat oblique to the different times we've distinguished so far. So we have yesterday in particular distinguished between the physicist's time and the psychologist's time. And we have asked the question whether perhaps there is a third time, a philosopher's time, which generally was rejected as unnecessary. Now, I take it with Ellie and others that one of the central tasks of a philosopher is to reconcile and to understand the relationship between the manifest image, the world as it manifests itself to us in our experience, and the scientific image, to use a distinction introduced by Wilfrid Sellers, which is what our very best physics tells us the fundamental structure of the world is. These seem to be in tension, and that's an interesting tension, and this tension is very much, to relieve that, to understand that, is very much the job of philosophers, I think. In much of my work, I am concerned with understanding and articulating, to some degree, even the scientific image, that side. So I'm interested in that sense in understanding the physicist's time. That's my primary task. Now, that's the sense in which there might be one time. There's one physical time. isn't that the most obvious, most straightforward, most fundamental, most incontestable fact there is about the structure of the physical material world? Or so think many people. For instance, here's Clarence Clark, who expressed this sentiment, saying that what could possibly constitute the more essential and more ineliminable component of our conceptual framework than that ordering of phenomena which places them in space and time. We could imagine a world without electric charge, without the material atomic constitution of matter, etc., etc. But a world not in time, a world not spatial, except to some Platonists, that seems a completely unacceptable idea, or a world really devoid of any being altogether. Remember Aristotle's definition of what it means to be. To be physical or material object is to be in space and time. So obviously that presupposes that there is space and time there, somehow in which you can exist. So if there's no space and time, there could not be such being, it appears. So that's the sense in which you might demand that there be one time in the physical world. No more, no less than that. Okay, now I move away from this intuition, and I'm introducing what is one of my central research focuses, and has been for a number of years, namely to study quantum theories of gravity and their philosophical foundations and their philosophical implications. I think it's a very rich field, philosophically speaking, not just scientifically speaking. Now, the first question you might ask is, why on earth do we need quantum gravity? General relativity, which is our best theory of gravity and the space-time structure, seems to be a very, very successful theory. Has been tested many times in many different ways, always found to be true. Predicted recently spectacularly the existence of gravitational wave, or the detection. The prediction was earlier, but the detection happened recently, awarded with Nobel Prizes and the big Gregorian, etc., etc. So why would we want to replace that? Well, there is one reason at the end of the day, and this one is decisive. It presupposes that matter is classical. If we've learned anything in the physics of the 20th century, then it is that matter is not classical. Matter is quantum. And if a theory cannot take this fact on board, then it seems like there has to be some other theory that's more fundamental that can do that. So I take that as a sufficient motivation to go beyond GR and to look for a more fundamental theory of gravity. And that would be a quantum theory of gravity. I don't mean any specific research programs, any idea that will be a theory of gravity that can deal with the quantum nature of matter, I will happily call quantum theory of gravity. Good. Now, as you may have heard, there are very many different approaches, and unfortunately, very little, if any, experimental data that somehow seems to constrain the search for such a theory. There's most visibly string theory, which is predominant, at least in the number of physicists who work with that approach. It's a way of extending principles that have proven itself in high-energy particle physics to incorporate gravity. That's this research program, but there are others. There's loop quantum gravity, for instance, non-commutative geometry, causal set theory, quantum gravity based on shape dynamics, many, many different ways of approaching the problem. Some of them starting out more from particle physics and quantum physics in general, trying to incorporate gravity from that side. Others are starting out from general relativity and identify what they take to be the central insights and lessons of relativity and somehow extend them in a way so as to articulate the quantum theory of gravity from that vantage point. I will be looking today at loop quantum gravity in particular. Now, don't worry, I will not try to sort of teach you everything about loop quantum gravity in just a few minutes. But I'll show you one interesting sort of model which has been based on that approach, which leads to what I will be talking about. Anyway, so there are all these different approaches, and it's one of the, so the book that was kindly mentioned by Alessandra, and I was co-writing with Nick Huckett, Out of Nowhere, The Emergence of Space-Time and Quantum Theory of Gravity, out from the realization that as these different research programs may be, they seem to suggest that to some degree or other, in some sense or other, space and time are not part of the fundamental furniture of the world anymore. These are theories which postulate as fundamental structures which in some sense are not temporal or not spatial. The way they do this is different in each research program. The degree to which these fundamental structures are non-spatial temporal is different in all these different research programs. So I hope this is understood for now, but one point that I'm very interested in as a philosopher is to imagine this, how it would be if this is borne out, if really the fundamental world is non-spatial temporal. What would that mean? Could we even do science in such a way? Could it exist? Why would it, these sort of questions, that's the central focus of what I'm working on. Okay, and that seems to be important because, as I've said already, these quantum theories of gravity would be more fundamental than general relativity. And therefore, in that sense, they could hold or claim metaphysical priority over whatever we've learned or thought to have learned from general relativity. Okay, so I've already said this. Now, this is the sense in which there may be no time. Okay, if that's borne out, then there is no time, at least not at the fundamental level. So I've explained, in some sense, 2/3 of my title. To explain the third part of the title requires a bit more work. Anyways, this is the general project I have with Nick. So here's the thesis wrapping up that part. Space-time, according to these quantities of gravity in general, and according to loop quantum gravity and cosmology, which is the one I'm concerned with today, is not fundamental. We have a problem of space-time. How can we understand the world in which space and time are emergent phenomena as opposed to fundamental existence? So there must be some way in which space and time, to the extent to which they exist, emerge from that non-spatial temporal structure. That emergence cannot be, as it's sometimes used in English, emergence as a dynamical process, as a process over time. Something emerges over time, it sort of comes into being over time. That cannot really be a coherent way to think about this here, because time itself is going to arise out of this. So this must be an atemporal, a non-temporal form of emergence in which space-time comes out of that structure. Here's how you should be thinking about this. It doesn't mean space and time. This is my representation of space-time, the two galaxies. It's an expanding world, I suppose. The galaxies are receding from one another. So that's not real. That's not the idea. Of course, space and time exist in some sense, just as tables and chairs exist. It would be folly to deny the existence of tables and chairs and things like that. I mean, there have been philosophers which have done this, of course, but I think that the reasonable position is not to deny that these things exist, even though, of course, they're not fundamental. They arise out of some sort of serendipitous combinations of more fundamental constituents to form these very ordered structures that we observe. It's in a way similar to the way liquid water emerges out of something that's more fundamental than it, and which is not liquid and does not have many of the properties. The liquidity of the water really only emerges from fundamental constituents of water, whatever exactly they are, in a way, only if these fundamental degrees of freedom combine in a sort of the right way to make this liquid water. You're supposed to be thinking of the emergence of space-time in a similar way. If the fundamental non-spatial temporal degrees of freedom combine in just the right way, they will form space-time. But it's not necessary. That means there could be, in accordance with the laws of nature, the fundamental laws of nature, being combinations of these fundamental degrees of freedom which would not give rise to space and time, just as there are fundamental states of the constituents of water which do not have, which are not in a liquid phase, which are not liquid water, of course. Okay, so that's the general picture here. Now, if you do loop quantum gravity, is going to be a fundamental theory of gravity. And one thing, there's two things you might want to understand when you do quantum gravity. You will want to understand certain astrophysical phenomena. You will want to understand black holes, for instance. Many people believe that quantum gravity will give us a fundamental theory of black holes, and we will finally understand how these are supposed to work. But also cosmological phenomena. The Big Bang in particular, the very early universe. That's a period, a phase, a part of physics where it seems to be important to consider quantum gravitational phenomena. And this is the one I'm going to be interested in. So how can we model, how can we think about the Big Bang if we have some sort of ideas about fundamental quantum theory of gravity? And that's the way in which we will see there's a temporal emergence of spatial temporality, which is different from an atemporal emergence. Let me explain. The reason is that the very early universe is a way in which the fundamental degrees of freedom of quantum gravity will not really coalesce into a space-time structure. They will be in a wild quantum state where they have no well-behaved spatial temporal structure. But in the later universe, of course we do. We know that. This is one of the constraints, clearly, that we must recover that. Today, and for a few billion years now, we have a pretty well-defined spatial temporal structure, which is to an extremely good approximation described by a model in general relativity with some additional assumptions that we introduced from outside of general relativity, from particle physics in particular, give us a model of cosmology which can deal very well with the large-scale structure of the late universe. And late, I mean after the first tiny, tiny split second. But to understand the tiny split second, you need quantum gravity. Now there's a sense in which that split second, the quantum gravity phase, is earlier than the later times at which we have well-defined space-time, right? So there must be, it seems, a temporal relation of earlier than and later than between the non-spatial temporal Big Bang phase and the later phase, the spatial temporal phase. So that suggests there's something like a transition from a non-spatial temporal state to a spatial temporal state. But that transition, in some sense, is temporal, and yet it's that transition which only gives rise to time. Okay? So the question very clearly is for a philosopher, how could that be? How should we think about this? How can there be a transition or a change without time? There seems to be a process before and after. Now, there are a number of examples of quantum theories of gravity where something like this seems to happen. One is Daniele Oritti's geometry genesis, which is a particular approach, partly based on loop quantum gravity and on other algebraic methods. There's string quantum cosmology, there's cosmological models based on string theory, and there is loop quantum cosmology, which is what I will talk about. Okay, here are some of the references where we talk about some of these aspects. Okay, good. Now, so we should distinguish two questions, really. The first question is then, how can a classical relativistic space-time or space and time of our experience, which I understand are not the same thing, but I'm taking for granted for the purposes of this talk that once I understand how to get classical relativistic space-time, I understand how the phenomenological space-time can arise. That is, of course, a highly non-trivial connection there to be made, but it's not the concern for this talk. Either one is going to be good enough for me, really. But that thing has to somehow come out of a fundamental non-spatial temporal structure. That's the first question. And the second question is then, how can the universe, which is fundamentally non-spatial temporal, evolve in some temporal sense from a non-spatial temporal phase to a spatial temporal one? And that may be in some weird way the way in which we have perhaps two times. Okay. Now let me try to illustrate this. I'm not going to give you equations because I believe I would not be able to convey the ideas by showing you equations. I'm going to show you pictures. The pictures have to be taken with a grain of salt here. They're approximate representations of what I take to be the central essential ideas, but they're not a precise representation of the mathematics. Just so this is understood. Okay. Anyway, we have this non-temporal emergence. We have some sort of structure, whatever that exactly is from quantum gravity, that gives rise to a smooth space-time. This is a relativistic space-time consisting of a manifold and a metric. You don't know what that is, don't worry. Relativistic space-times come out of this. Okay? Now, I can represent these space-times by so-called conformal diagrams. This is a very nice representation of a relativistic space-time because it directly gives me the causal structure. The idea is that time to first order goes up here and space goes left and right, but really what is captured is the causal structure, meaning the light cone structure, by saying that light will always go on 45-degree angle trajectories here. Now this is a model of a representation of a cosmological model. It starts with a Big Bang singularity, and then it evolves forever, presumably. This is future infinity here. It just goes on forever. Now, one thing that's really not represented very faithfully is the fact that this is an expanding universe. It looks like a collapsing one from a gigantic Big Bang to an ever narrower future. Spatial scales are not faithfully represented in that diagram. That is actually, in fact, the opposite is true. It's really an expanding universe. Anyway, so the one thing that is important about this model is that I can introduce what we've seen in Carl's talk, for instance, a preferred foliation, a cosmic time. So each of these slices, however twisted they look like, they're really slices of cosmic times, of simultaneous coexistence of the whole universe, a snapshot of the universe at the time. This introduces a slicing like that, which can be ordered with a time, and you can introduce a time. This is a sequence of time, an ordering of subsequent times. So this is my color code. Red means non-temporal relation, emergence. Green means something like a temporal direction, a temporal production, a temporal earlier and later than, maybe a temporal emergence if you want. Okay? And I'm going to stick to this color code. Good. Now, loop quantum gravity is a beautiful way to apply standard quantization techniques that have been successfully used in other theories to general relativity. The problem is general relativity is a little bit different from these other theories that we've tried that procedure beforehand, which makes the procedure technically extremely difficult. And in fact, it cannot be, to this day, really be completely done. It cannot be completely executed. There are many smart people, very smart people working at this, and still they have not managed to completely execute that program. They get stuck in the middle of it. They have some idea, some adumbrations of what the fundamental structures will look like, but they cannot complete the program. Now, what do physicists do if they're stuck like that? If you don't want to give up the research program altogether, then you have to come up with some way of simplifying your equations so you can still do something. So you try to formulate toy models where you make simplifying and idealizing assumptions. And one assumption that really presents itself as perfectly natural is you impose a symmetry of a homogeneous, spatially homogeneous and isotropic model, which is what our universe is believed to be at sufficiently large scales. So you look, in a way, at what you think may be the cosmological sector of the theory. That turns out to really simplify the equations, and you can get a much simpler theory, which is now known under the name of loop quantum cosmology. This is a technical explanation of what it is. It doesn't matter so much. It's a very, very simple model. The idea is you have 1 degree of freedom. That's just, it's one physical property of the universe, and it's its size. That's the only thing there is. It's a scale. And that scale changes over time. That's the only thing that can happen. So clearly this is way too simple to understand our universe, but it's a start, you know. If you get on into mathematical troubles, you have to be modest in your goals, I suppose. So you study these models. You study what can happen when you have these models of one scale in this theory, and what you find is that if you think of that scale factor as running over time and giving you, in some sense, a measure of the time, you find, this is again a mathematical simplification, then it becomes a difference equation rather than a full differential equation that can't be solved. But the important and interesting thing is that it turns out that the evolution near and at the Big Bang is well defined. You can actually say, hey, here's something like the Big Bang, namely a moment in time where, the universe's size vanishes. But you still have a well-defined evolution through it. That's not the case in general relativity. In general relativity, the Big Bang is really a singularity, which means the equations, they're not well defined anymore. You cannot define an evolution through the Big Bang in the Friedmann-Lemaitre-Robertson-Walker space-time. Here, that seems to be impossible. So you can now ask, I would really like to know what happened before the Big Bang. Right? That would be an interesting scientific question. All of a sudden, now this is an option, when in classical GR this was not a meaningful question. So I'm going to explain to you what happened before the Big Bang. Here's what happened before the Big Bang. We have this cosmological model. There's some sort of fundamental, discrete, somewhat non-spatial temporal weird structure here that corresponds to the late phases of the universe, where this is the spatial temporal phase as well approximated. So I can impose, I can identify what I should take based on the time here, the green arrow here. I can identify what I should take as a sort of a substitute for time in this model. There is something where I can do that. So I have a little green arrow there. Now, what I do is I sort of evolve mentally backwards using that identified arrow that's well defined all the way back here in this model. So that gives me a temporal orientation. and until I go so far back where I get to something like that which corresponds to the Big Bang. Now here we know this is not going to give rise to the Big Bang in the classical sense. For this, the classical is not going to be a good approximation. So that here the red arrow will be invalidated. The interesting thing is I could go past, as I already said, to earlier times following this same arrow backwards here. Okay, good. And it turns out that there's a certain symmetry. So this is like, as Julian would call it, the Janus point here. So there's something similar that you see in these models, qualitatively similar. You have some sort of special state here, but over down here you have something that looks just like the mirror image of what you have up here. It looks like what you have is this flipped around. Something like that.
But your arrow is always going in the same direction.
Well, I'm going to get to that. I'm going to get to that. We're going to have to sort our arrows here. Okay. Now, one interesting thing is that because this is a connected structure here, it seems like there should be some sort of connection at the large scale as well. Even though you have this embarrassing phase here where you don't really know what happens, and the classical models are not going to describe it well. And this is a representation of the classical model, so I sort of blacked this out to indicate that for this point, this is not a good representation. Now, if that green arrow here is as it was over here, I'm using this to infer the direction of the green arrow here. If that's the right way to think about it, what I should be thinking about this is a model of a collapsing universe that goes through some sort of quantum gravitational phase of a Big Bang and then re-expands. This narrative makes sense because I have a well-defined arrow throughout all of this. This is the green arrow is time, remember? If that's the right way to think about it, then this is what's happening. If time isn't fundamentally there, it emerges via the collective behavior of the fundamental degrees of freedom as a result of some richer physics, presumably. This is a super simplistic model. Then it may be that maybe through the emergence of the increase of complexity, or because a system with many degrees of freedom is really getting out of equilibrium or closer to equilibrium, as the case may be, depending on how you think about entropy and all of that at the global, the cosmic scale. If that's how you think that really time is arising, and the fundamental parameter, the green arrow on the left side I showed you here, is really not, is only with some limited validity a representation of the real direction of time. If time instead emerges in a more complicated way here, in a fuller model, then we have to be careful about the direction of time that we assign in the models I've shown you. Then presumably time for any part of that model is going to emerge just in the way before and after the Big Bang in the same way. Now, if that's so, then plausibly, given that they're mirror images, the direction of time will be away, pointing away from that sort of special state, the Janus point, or the Big Bang state, or something like that, in both directions. Which means the narrative I've given you of a collapsing and re-expanding universe is misleading at best. Basically, it's just false. This is not what's happening. Because I cannot give this way type of reasoning. In fact, what I have is, as I said, pointing away, I have time pointing away from the Big Bang in both phases. Which means I was too hasty over here when I identified the arrow of time in the fundamental structure as uniformly going in one direction like that. And to be coherent, I should flip this around as well in my interpretation now. Now the narrative is different. Now the narrative is going to be, I have maybe something like a very special state, the Big Bang state, or something that happens there, from which two universes are born. It's the twin birth of universes, or the birth of twin universes. Maybe that's the best way to put it. Which are like mirror images from one another. Okay? Now, they're perfect mirror images in this very simplified model. But of course, the model is unrealistically simple. This is not going to be the full story. If we want to have some interesting evolution structure, we have to add many more degrees of freedom. We have to really study much more complex and much more realistic systems, in which case, presumably, we're not going to generically see a perfect symmetry here. But the suggestion is, nevertheless, that sort of qualitatively, to some approximation, we will see something similar. We will see a process of structure forming away from that special state in both directions. So I should note an important part of that sort of train of thought that I've presented here is that I've used green and red arrows to change side and go up and down on each side. And really, when I do that, I have to be very, very cautious, because the red arrows, unfortunately, are not sufficiently well understood here. The red arrows in Loop quantum gravity generically, and as far as I can tell, in any other approaches to quantum theories of gravity, are not completely understood. It's highly non-trivial to actually, in full generality from these theories, understand how space-time structures emerge from these fundamental, maybe 11-dimensional M theory, or from the full loop quantum gravity. And part of this is because we don't have the full theories yet, but part of it is also that it's going to be very difficult. In the case of cause-and-effect theory, to give you another example, that program is not completed either. It's not a quantum theory. This is a classical theory of some sort of discrete space-time. And there, it cannot be understood how generically from these causal sets we have something like space-time emerging. In a way, we have way too many ways in which these fundamental discrete structures can combine, almost all of which, in a mathematically precise sense, do not give rise to anything spatio-temporal. So clearly, the red arrow there is not understood how that's going to work. Something more needs to be done. Maybe, I would conjecture, not everybody agrees with that, but I would conjecture, because this is also the emergence of classicality, of well-defined, determinate spatial-temporal structure out of a quantum structure. Part of understanding the red arrow will also be understanding the measurement problem, the quantum measurement problem. In general, how can we have determinate classical solutions or outcomes from generic quantum states? This is even in non-relativistic quantum mechanics, which is the simplest possible way in which we could formulate a quantum theory. It's not fully understood how that can happen, let alone here. So how is it that, I mean, maybe one other way to say that is that if this is a quantum theory, we would expect something like the generic states of these things will be superpositions of structures that you can characterize classically, of different, maybe connectivities of different network structures and so on and so forth. But if it's generically, the fundamental state is a superposition state, and we seem to have determinate geometrical properties of the emerging space-time, we have to understand how these superpositions can somehow collapse into determinate states. That's going to be a challenge, because one thing that does not seem to be working here is whatever answer you had for the standard quantum mechanical measurement problem that involved observers. If you thought that it's necessary to have an observer interacting with a quantum system to collapse the quantum state somehow, then that seems to be impossible to apply here, because we're talking about the cosmos here. There's no outside observer that collapses that state, so clearly there must be, if it's a collapse mechanism, there needs to be some other intrinsic, spontaneous collapse maybe that works. Maybe we can understand it in a Bohmian way, so that there is, after all, truly, really only one way in which this structure is connected, and that's somehow supposed to solve the measurement problem. There's a question how that can be made compatible with relativity, which presumably is necessary here. Or maybe we can understand a sort of an Everettian picture. I'm not sure. I mean, I really don't know the answer to that question, but I think it's going to be part of fully understanding the red arrows. Okay. So let me summarize. Oh, okay, this is more time than I thought. Great, I can really take time in summarizing what I take to be the most salient points that I've said. Okay, moving to quantum theories more fundamental than general relativity. These are going to be quantum theories in some way or another. By the way, maybe one thing that could also happen is that we have a theory which goes by the name of semi-classical, where we think that the geometry of space-time is still classical, but it connects not to classical matter as in GR, but to quantum matter. And we articulate how that connection is supposed to work. That's one proposal. That seems an extremely conservative proposal, that maybe as such is very welcome, because quantum gravity is such a hard problem with so many bells and so many so many parameters you can vary, so much freedom in how to articulate such a theory, that maybe it's a virtue to stick as close as you can to what we've got before. But there are some problems with that proposal as well, because it's not so clear how to incorporate an interaction between classical geometry and quantum matter, which seems to be something you need in general, sort of a general relativistic way of thinking about gravity. Okay, so if you go to these theories which you think will be giving you a fundamental view of quantum gravity, it's generically the case that these structures are not spatio-temporal in the full sense that the structures were in GR. As I said, this is an important point. The qualitative difference, spatio-temporally speaking, with general relativity is going to be depending on the particular approach you take. It will differ from approach to approach. There are some proposals where you just have no time, but you more or less have space, at least not too remote from what you thought. There's going to be other proposals where you have more or less something like time, but really nothing like space. And there are proposals where you just have abstract algebraic relationships which are not directly interpretable in any geometric way, where you have to say there's no fundamental sense of space-time left. So in group theoretic approaches or non-commutative geometry, things like this, that's not interpretable at all in spatial-temporal sense, in a sense. So we will have to understand, therefore, as a very central task of that relationship, how these non-spatial temporal structures connect back to something that looks at least sufficiently spatial temporal, right, as we find it in GR maybe, or some subset thereof. Okay, so that would be a central part. But as it turns out, there's models of quantum gravity where, in a way, there's two ways in which temporality arises. One way is that there is this atemporal relationship characterized by the red arrows that I've shown you. It's some sort of, philosophers might say, of dependence, perhaps. Certainly supervenience, but arguably something more, between the fundamental non-spatial temporal level or structure and the non-fundamental but spatial temporal structures. So space-time, relativistic space-time or something like it is grounded in something that's non-spatial temporal. That's the way, one way in which temporality arises, through the red arrow. But in a cosmological model, it seems as if there's also the green arrow, and the green arrow suggests that there's something like a transition from a quantum state, which is not interpretable as a snapshot of the spatial structure of the universe at the time, but nevertheless is considered earlier than, I should put quotes on pretty much every second word here, earlier than later states for which there is a well-defined spatial structure given of the universe. Okay. Good, yes. So there's these two ways in which temporality arises. Now, my title has mentioned 2 times. That's misleading. The idea, of course, is not that at the end of the day, we were somehow left with 2 physical times. That's not the idea at all. There is 1 physical time. It's just that there's a sense of earlier than later than which somehow gets extrapolated, read into the non-spatial temporal structure, even though it's an extension of one and the same sort of temporal relationship. Okay. Now, in the model of loop quantum gravity, loop quantum cosmology, I analyzed the relation between the temporal and atemporal wave, characterized by the green and red arrows, in which relativistic spacetimes can emerge from an underlying non-spatial temporal quantum structure. And I suggested that we should think of this transition from the earlier quantum state to the later cosmology, more or less classical cosmology, as induced by an emergent, temporally located direct physics of the later universe. So it's derivative of that, as it were. This implies that the cosmological models, like the one I presented, should be thought of as modeling the twin birth of 2 universes rather than a collapsing and then re-expanding universe. Okay, that's it. Thank you very much.
Okay, Elvira, Università. That was very interesting and clear. So I think I have a naive question, so I will apologize in advance. So it has to do with the very starting point of your talk. So when you said that there are 2 images, I mean, of reality that you can be interested in and manifest images, like cellars, essentially. And then you said that you are interested more in the scientific image of the world. And so this is why you decided to put the 1 time in the title, right? The expression of your title of your talk is 1 time. So the time you're interested in is the scientific time, let's say that. And then you said that according to a theory, namely the quantum theory of gravity, the space-time properties disappear. They are not, they're not constituting the reality, right? They are not fundamental, kind of. Right?
Yes.
Is what you say. And then you wanted to explain how exactly then time, that temporal spatial or spatial temporal properties emerge from the fact that they are not fundamental. So they don't constitute the reality, but they emerge, right? And so my question is, why is this a project which has to do with the scientific image? Because the scientific image is already telling us that they are not fundamental. So your project seems to be something like from a different perspective, like you want to understand how they yet emerge, even though the theory you are using, the scientific theory, is telling us they're
Yeah, okay, fair enough. So maybe I should start by saying that it's not that I'm just interested in the scientific image. I'm very much interested in the relationship between the two, but in the spirit of a division of labor, in my research, I tend to study more the scientific image. And as part of that, I study quantum gravity. And there you're quite right. I noticed that it's at least a serious possibility that the fundamental structure, as best described by our best science, may not be spatial-temporal in the way we thought it is. Now, that makes it urgent for me to understand how that relates to the spatial-temporal world, either as it's been postulated in previous scientific theories, and in that sense it would be a question of a relationship between theories in the scientific image of the world, or how that fundamental structure can give rise to beings that have experiences as of, space and time, spatial and temporal relations, temporal passage perhaps, and so on and so forth, which would be a connection between the scientific and the manifest image. So this is the way in which I said, for the purposes here, I don't care too much which of the two will eventually turn out to be the way to go. Two more remarks. One thing is, if I understand the relationship of these structures to relativistic space-time, so the relationship within the scientific image, then I think whatever I already did beforehand in understanding the relationship between the classical relativistic space-times and the psychologist's time, perhaps, or the time of the manifest image, can be applied and used, because that would still be valid, because I've now connected the fundamental structure to these space-times. So to that extent, that work would still, of course, obtain. There is a second possibility which I'm also interested in. I have not talked about this. I have published about this, but it's an extremely interesting suggestion, namely that the fundamental structures may bypass these classical relativistic space-time. They may not give rise to every aspect and every property of these classical space-times. They may only give rise to something reduced from that. That is, however, sufficient, of course, it better be sufficient, to account for all of the phenomenology of temporality. Yes, and now if that's the case, that means we have to identify very carefully what do we take to be the sort of things that the functional roles, as I would put it, of space-time in explaining the phenomenology of temporality. Surely there's going to be some sort of like temporal ordering, there's got to be something like temporal duration, spatial distances, maybe the relative location of things in space. So all these things, that's what space-time does, right? It does all these different orders that seem to be important. So, but maybe we should not care about recovering relativistic space-times, but we should care about giving a very tight and clear argument of how these fundamental quantum gravitational structures can fulfill all of these roles. If we can show that in some sort of direct way, then I think we would be space-time functionalists, I would say. We would sort of not say space-time has to be posited as a thing that exists somehow or something like that. But we have to think about what are the roles, the functions of that thing that we need to recover somehow, and that would then be sufficient.
Yes, Mauro, please a short answer.
Sorry.
The question is to be short.
Yes.
What kind of notion of law you have in this red act? Because laws are typically defined as, say, differential equations and initial conditions, but you cannot have initial conditions.
I don't have differential equations, you say?
Yeah, but look at, you have this dynamical in the square. So
That's good. That's a good question. Now, when you start from general relativity, you have what people often call dynamical laws. The Einstein field equation. That's often considered to be a dynamical law. And there's some dynamical aspects in some way from that because it's a relationship, point-wise relationship between the matter-energy content of the universe and the geometry of the universe. But is it really a dynamical equation? If it's a dynamical equation in the usual sense, it seems that we presuppose that there is a spatially extended physical system that somehow evolves over time, different states, having different states at different times. And this is what the dynamical equation describes. In GR, that is only the case in a limited sense. It's only interpretable in that way in a special kinds of models of GR, not in general. So maybe already there we should sort of step back from a too dynamical interpretation of that equation. Now, when you apply the canonical quantization procedure, what you do is you have to split up the Einstein field equation in a way. And and you get certain additional equations which are called constraint equations, which need to be satisfied in order to make sure that the system you're looking at, the way you describe that system is equivalent to what you had before. And one of these equations says that the Hamiltonian constraint, the Hamiltonian function that you define then is zero. It has to vanish. Now, what you do when you do a canonical procedure is you sort of make these functions, or these equations, quantum equations. You try to formulate the Hilbert space, a space of states, and you then apply these functions as operators on the states, so these states have to satisfy these equations. And because traditionally, classically, we said that the Hamiltonian equation is a dynamical equation, the Hamiltonian function is that which generates the dynamics in those cases, and there's a formal analogy here to the dynamical the Hamiltonian equation, we have the Hamiltonian constraint equation, we say that this is like a dynamical equation. But it's a bit puzzling because it says it's zero, which means there couldn't be any temporal evolution of any gauge invariant quantities in the fundamental physical theory. So again, it's puzzling why this should be even considered a dynamical equation. Now, however, here too, under certain circumstances, simplified circumstances, you can think of this, there is a reasonable natural way to interpret it as a dynamical equation. And this is the equation which then gets simplified in the loop quantum cosmology to a near difference equation, which really relates the states at different times, at different sizes of the universe to one another through that equation. And so if you're given the universe, this is an oddity of this, you actually need the size of the universe at more than one state. You need it at 3 states, at 3 moments in time, to then determine the size of all the others. So in that sense, it's dynamical. But again, it's with a grain of salt that you should think of this as dynamical. Now, okay.
Be longer.
Sorry. Yeah, I should know what
We got that card, and the other one?
I have a comment mostly because the budget of my particular is talk in general. And probably it's our fault as physicists, because we are friends theorists. They produce theories. Since they have theorists, they produce theories. But a theory is a misleading word, in the sense that in physics we consider a theory something that has been validated by experiments. Because otherwise we call it conjectures. And I would suggest to use conjectures, which is much more, let's say, appropriate to explain models that have not been validated by any experiment so far. So, coming back to the issue of having quantum gravity theory, meaning a theory that will be validated or have been validated by evidence, observations. So today we have maybe 100 of these conjectures. Maybe I'm underestimating the number. And some of these conjectures imply that time is not a basic component of the laws of our universe. Again, are some of these conjectures, and in a population of conjectures that contains completely different approaches. And none of them have been validated. So, my issue is, it's good that we elaborate on the possibility that time is not really a key component of our universe. But today, we have to start from the point of view that for what we know today, time is an essential component to explain our universe today. Tomorrow we'll see.
So I certainly agree with your comment that this is very conjectural, it's very speculative. None of this is empirically confirmed. That's absolutely correct. Now, what does that mean? I mean, one way to understand your question is, should I, as a philosopher, then care to study these conjectures, these very speculative ideas? I think, yes.
Otherwise, you risk to lose a lot of time, because if 10 years we discover another solution, you have lost the 10 years of time.
That's right. So I run, by looking at these theories or speculations, I run the same risk like the scientists who work on these things. It may turn out to be completely misleading, completely false, and people will abandon it. That's absolutely a possibility. And if that happens, some of the things I said, and the ways I try to think about these things, may be obsolete as well. That is absolutely a risk, but it's a risk I accept, because I do think that this is philosophically exciting, what's going on. And for me, as a philosopher who's interested in the foundations of physics, this is really cool stuff, and I'm not going to be stopped from studying it, even though I understand the very speculative nature of the physics.
Very quick question. At the beginning, you basically talked about two ways in which we understand existence. Existence in space and time, or a Platonic sense of existence. And you told us the whole story that isn't the former, so would you accept that essentially the starting point here is a mathematical abstraction, and hence it's sort of like Platonism or Hegelianism or something like that?
It's an excellent question, and my answer is a strong no. Absolutely not. I think what it suggests, however, is that the Aristotelian criterion of existence, or of material or physical existence, has to be extended. In a way that what we're doing here is not mathematics. We're not somehow sort of arising from Platonic heaven or falling down from Platonic. I'm not sure what the right picture would be, but this is not at all what's going on. These are physical structures, the fundamental structure of the physical world that happens to be describable by mathematics. It's physical by virtue of giving rise to space-time and giving rise to the world as we know it. By virtue of that connection, it is physical, and in the sense I have to extend my definition of what it means to physically exist. I don't want to be a Platonist or a Pythagorean.
Julian, the last question.
I have this one to be quick. You presented these Janus-type arrows. Is that what people like Abhayashtakar are saying? And if so, when do they start saying that? That's your introduction. I mean, let me just say it's interesting. 4 years ago, I started interacting with David Sloan, who did his PhD with Abhayashtakar. And in the course of a walk around the university parks in Oxford, I persuaded him there must be Janus-type arrows. It hadn't occurred to him working with Abhay on his PhD thesis.
Yes, I agree with you and not with them, and I don't think they think of this in these terms. Whenever you read Abhayashtakar or Martin Boyle, these people, they tell you something of a collapsing universe that
and bounce.
Yes, of a bounce.
And time goes on in the same
exactly,
way.
Always. In fact, I think it's the wrong direction. I discussed this with Colin O'Reilly on one occasion, and he's very open to that idea. He thinks this is a real possibility. But many of the people actually working in technology don't think of it that way. And I think they ought to, because for similar reasons I think that you have absolutely.
No, mine was just a comment on your comment. Science is part of science going ahead with conjectures. And after all, it was a big conjecture by Darwin to imagine that there was something like an evolution of the species, not knowing anything about the fine mechanisms. And it took almost 100 years to discover these mechanisms. But the push of the theory...
He made remarkable observations first.
He started
from the observations.
No, sure.
And the mechanism is not known. Not known now.
Well, the static word mechanism was DNA, but...
It's wrong.
But
it's incomplete.
That's great, yeah, but it's part of the science going back, pushing forward through conjectures.
Yes, providing you start saying it is a conjecture.
Yeah.
Because otherwise,
let me be very clear. This is conjectural, this is speculative. All these approaches are to some degree based on reasonable physical principles that have proven to be fruitful elsewhere. But they're consistent, usually, but we don't know whether the extensions are going to be working out. We just don't know.
Thank you, Chris.
Well, but that's the whole point of this kind of thing. It's about dialogue.
I will come back to that.
Yeah, when are you speaking?
Tomorrow, domani. Sono l'ultimo domani.
Domani?
Domani mi hanno detto che
No? Now we have the last talk of this morning. I'm glad to present Rocco Ronchi, which is a philosopher, full professor of theoretical philosophy here at the University of l'Aquila. Since his PhD, he has worked on Bergson philosophy, and in the light of this yearly study, but also following a work of deepening speculative theology and classical metaphysics, he has developed a research project aimed at identifying what he calls the minor canon of Western thought. It is characterized by the affirmation of the most rigorous immanence, and it constitutes an alternative to the dominant anthropological existential paradigm of the continental thought. Among those belonging to the minor canon stand out the name of Plotinus, Spinoza, Bergson, Whitehead, Gentile, Ruyère, Deleuze. His current research interests include philosophy of nature, speculative metaphysics, radical empiricism, philosophy of process. He is the author of several essays and volumes, among which I recall Minor Canon, Canone Minore, Gilles Deleuze, Credere nel Reale, Believe in Real, and Bergson, Synthesis. Yes. I'll give you the floor. His talk's title is Peter and Paul, a ghost story. We'll come back to Bergson and duration and simultaneity.
Thank you, Alexandra. Before beginning, as a co-organizer of this conference, let me say just a few words to thank all those made this conference possible. Obviously, our rector, Paolo Inverardi, the rector of the Gran Sasso Science Institute, but a very, very special thanks to the dean of our department, Simone Gozzano, who has accepted to play the role of Bergson, and so my gratitude is has grown, and a very special thank to Alessandra Campo. She is at the source of this conference, at the origin of this conference, and a special thanks also to all our research fellows who help us to realize this conference. And last but not least, thanks to our colleague and friends who accepted our invitation, and we thank enormously for their generosity. And I begin. My topic is duration and simultaneity, durée simultanéité. The Bergsonian book on relativity. And duration and simultaneity, 1922, is a very strange thing. It's a ghost book that tells a ghost story. And it's a ghost book because it appears like Bergsonian books. After the 6th edition, 1931, it disappears. It disappears at the request of the author, and it returns later, but it returns as a ghost, as a phantom, as like a revenant. It's not clear, in fact, where to place it. It's not clear for the Bergsonian scholar. Eventually, it will find a place in the Mélange, 1972, and not in the Oeuvre, 1959, alongside the Bergson's official books. The 7th edition, 1978, contains a warning which must justify its reappearance in the French bookstores. It's not known if this book should have a Bergsonian paternity or if it has the nature of the symptom and the failed act. But DS, I call it DS from this moment on, DS is spectral also for another character. A reason for content, not just formal. If we browse through it, the phantom Edward returns continuously, almost obsessively. Phantom and all its relatives, ghosts, marionettes, empty puppets, virtual or fictitious beings, mirage that seem to have life and instead do not. A phantom ghost is one of the most used words by Bergson in his controversy with Einstein. Peter and Paul, the twins of Langevin's mental experiment, who in Bologna in 1911 had attracted the attention of Bergson, Peter and Paul, they continuously exchange the role of the ghost. If one acts as a reference system, then the other is dematerialized. It becomes a ghost. There is a dithy game of mirrors, a game that Bergson values because, as we will see, it will express the essence of relativity. There is a dithy game of mirrors. If Peter gives his eyes to Paul, then Peter can no longer look. He is only seen and does not see. Peter would no longer see himself as anything but a vision of Paul. Bergson writes in a very memorable passage which alone deserves a long comment. As seen by Paul, Peter would become a puppet. It is a phantom whose ontological consistency consists only in its being seen from afar. In the sophist, Plato calls what can only be seen from afar eidolon. Being ghost, being eidolon, is nothing but the pool appearing to, from afar. The Bergsonian interpretation of relativity, special relativity, is a Baroque theater. It is a theater of deforming mirrors, a theater at once comic and uncanny. A comic effect, according to Bergson's essay on comic effect, is produced when the observer perceives the inanimate, phantasmatic, virtual nature of those who move on the scene. Peter laughs when he discovers that Paul, who claims to be living, is just an inanimate puppet. A perturbing effect, according to Freud, occurs when what is most familiar suddenly turns into a stranger. Paul is the monozygotic twin of Peter. No one is therefore more familiar to him than Paul. But who actually returns from the journey on the projectile? Bergson answer, and please note which vertex of Baroque is reached with this note. Bergson answer, the Paul who gets out of the projectile on returning from his journey and then again becomes part of Peter's system is something like a flesh and blood person stepping out the canvas upon which he had been painted. And it is not Paul, the twin, who returns rejuvenated, but his virtual image. Who is back? The ghost of Paul is back. But be careful, Paul was nothing but a vision of Peter. So Paul was Peter himself, who had doubled into a virtual Peter, baptized Peter for convenience of analysis and presented for convenience of analysis as his twin. In the famous paradox, returning to Peter on earth is then the image of Peter himself, his imaginary double. The disturbing character of this impossible encounter is undisputable. In his answer to André Metz in 1924, Bergson explained, sorry, I have to change my... In his answer to André Metz in 1924, Bergson explains DS' philosophical meaning. He says, I am the first to recognize that relativity as a physical theory should not distinguish the virtual from the real. It is forced to put them on the same level. But, Bergson continues, I'm quoting, the task of the philosopher consists precisely in re-establishing this distinction. This is the purpose of DS. End of quotation. DS is a philosophical book. Its object is the physics of relativity, special relativity, but only to respond to the problem raised by the philosopher and not by the physicist. The problem is the difference in kind, difference of nature, difference in kind of the real from the virtual. Bergson writes, but the essence of relativity is to rank the real vision with the virtual vision. The real would be only a special case of the virtual. There would be not difference in kind. End of quotation. I remember that Bergson's use of the virtual lemma in DS does not have the meaning given it by Gilles Deleuze, although Deleuze takes it from his own reading of Bergson. Bergson makes in DS a canonical use of the term. Virtual, he writes, is the phenomenon subjected to an effect of mental torsion. Virtual, for example, is Paul depicted by the painter Peter at a distance, according to the rules of linear perspective. Virtual are all those phenomena that become possible in the light of a calculation conducted according to certain rules. In the case of relativity, it is that calculation that takes into account the need to preserve for every phenomenon, in this case electromagnetic, of the invariance of the laws of physics. In short, virtual is what would be possible if. What would happen to the simultaneity in the system S at rest if S is split into S in motion? What measures would Peter's reality have if Peter were to be split into Paul running towards the moon with a speed slightly slower than that of the light? With the question concerning the difference between the possible and the real, we arrive at the core of the S. We must always remember Bergson's philosophy is not philosophy against science, as is often said, and it is not a philosophy of science. Bergson's philosophy is rather philosophy with the sciences. In DS, DS is philosophy with the relativity. In DS, Bergson philosopher with Einstein. In DS, then, it's not physics, but the metaphysics of relativity that is called into question. The metaphysical problem of relativity is for Bergson a modal problem. The metaphysical problem is the difference in kind of the real from the virtual. Bergson writes, but the essence of relativity is to rank the real vision with the virtual vision. The real is only a special case of the virtual. Ultimately, according to Bergson, the metaphysics of relativity is Plato with Leibniz. There is a temporal world of ideas that is virtually given, and there is the real world that is only a contingent actualization of the virtual, a perspective. It is Plato because the concrete experience, the becoming, is explained starting from a supplementary dimension, purely ideal, visible only in the mind's eye. The actual perceived is replaced by the conceived, the becoming by the become, the real change, the change that takes place by what change, by what that change will have been once it is accomplished, which is a complete form. The Platonic idea is, in fact, how the thing would be given to an intuitive intellect that perceived it outside of time. The idea is the thing entirely unfolded. It is Leibniz, because by doing so, that is starting from the already done, from the factum, instead of doing theory, we have introduced infinite others ways in which the thing could have been built. And our real world, the one actually perceived, is now nothing but one of the possible worlds had the grace of exist instead of nothing, of not existing. We shall line, Bergson writes, we shall line it, our actually world perceived, we shall line it up wrongly alongside the others. We make no distinction between it and the other possible distribution, or rather, we see no more than an infinity of possible distribution, the real distribution being no more than one of them. End of quotation. This is Leibniz and the contingency of the reality. According to Bergson, relativity explains the real only as a special case of the virtual. One then distinguishes the philosophical discourse from the discourse of the physicist is then a question of modal height. Bergson is a megaric philosopher. Like Nikolai Hartmann, he assigns the primacy to the modality of real. The real precedes and grounds the possible, which becomes a shadow of the real, an imaginary projection, a ghost that is difficult to dissolve because man loves his ghost, as Hartmann says. Real means effective, wirklich. Fictitious means ineffective. It is called Alexander dictum. To exist is to have causal powers. The principle was enunciated in a solemn way in the passage of the Sophist, where Plato, by the mouth of the stranger of Ilea, polemizing with the idealist in the same line as Plato is ascribed by tradition, establishes the equation to exist equal to act or to suffer, even in a minimum degree, and by the action of the weakest of agents. To exist is equal to act or to suffer. To exist equal to cause. Only what causes an effect is effective. Bergson scrupulously adhere to this model definition of reality. What does then the philosopher who philosophizes with relativity do? Bergson says it clearly. Einstein's idea must be fully adopted and radicalized. We must completely embrace the Einsteinian idea. There is no privileged reference system, but we need to be more Einsteinian than Einstein. The Einsteinian idea, says Bergson, as complete, is philosophical and no longer physical. It must be said that Bergson not only fully agrees with Einstein in denying simultaneity in the instant, but finds Einstein as a valuable ally in his critique of the homogeneous time of classical physics. Milich Capek, in a very important book, according to me, Bergson and Modern Physics, 1971, wrote that no scientist would pay attention to the Bergsonian thesis when the idea of absolute space as the absolute frame of reference and the objective substrate of absolute simultaneity was still generally accepted. Things change after relativity. And it's amazing that Bergson's encounter with relativity went down in history as a fight. What teaching, in fact, is drawn from relativity? we can answer in Whitehead's words, there is no such thing as nature at an instant. There is no such thing as everywhere now. The limiting character of the velocity of light, implied by its constancy in all inertial frames, excludes the possibility of instantaneous interaction and absolute simultaneity. What then disappears with relativity, and above all, what takes its place? The instant disappears, and the instant disappears as a point devoid of thickness, as Aristotelian stigma, as Aristotelian nun, located in the absolute space contemporary to all the others present. The present disappears as instant to return as a field of presence, endowed with a temporal thickness, as spacious present, as William James says, or living present, as Edmund Husserl says. The present disappears as an unrelated atom, and it returns as an ongoing relationship. After relativity, there are no purely spatial distances at all. This is, Capek says, the tremendous ontological significance of the special principle of relativity. Where there is distance, there is relationship, that is time. Once again, the ancient thesis of the stranger of Elia returns. If time is real, time is dynamis, and dynamis is energeia, Wirklichkeit, and the effectiveness, the energeia, the Wirklichkeit, is koinonia, that is relativity. The simultaneity of flow, which is one of DSS's great conceptual inventions, does not, therefore, re-establish simultaneity. It rather identifies the condition of possibility of virtualization of real change, and therefore also of all measurements. I can project duration in space and count simultaneities in the instant. I can measure because my present is a duration, because my present has a thickness. It's, Bergson says, simul one and many. And because it is simul one and many, it can be articulated. In Whitehead's word, no consciousness lives in the atomic instant. We live in durations. In Bergson's words, the living present is a consciousness. That is an elementary memory. Bergson concludes, simultaneity of the instant and simultaneity of flow are therefore distinct but complementary things. Without simultaneity of flow, real duration and spatialized time would not then be equivalent, and consequently, time in general would no longer exist for us. There would be only each one's duration, end of quotation. To sum up, the simultaneity of flow is the condition of possibility of the traduction, of the translation of duration into the linear time with which we measure it. We measure time thanks to the simultaneity of instant, but it is the simultaneity of flow, that is to say the spacious present, that makes, says Bergson, that makes this measurement one of time. Let's come up to our question. What is time? We know how Bergson tells the genesis of his philosophy. One day he writes, I realized that none of the equations of science distinguishes the past from the future. The equation of Newtonian dynamics, Maxwell's electromagnetic equations, those of Einstein's relativistic gravity, share this timeless nature. They are all characterized by symmetry and reversibility. Regardless of entropy, the second law of thermodynamics, the more metaphysical of the laws of physics, Bergson says, the only law that allows us to distinguish past from future, time in physics did nothing, served no purpose. Now, what has no effect is nothing, Alexander dictum. However, Bergson continued, I told myself, time is something, so do something. Donc il agit, que peut-il bien faire? Bergson appeals to common sense. Common sense is often an ally of the Bergsonian argument, and responds, time is what prevents everything from happening at one stroke. Time is delay, or rather, it is retardement. I think in English, the act of delaying. Common sense puts us on the right track, but it is not enough. In fact, it could easily be adopted also by those who deny the reality of time. Julian Barbour actually mentions the Bergsonian answer to the question, what is time, but attributes it to John Wheeler, who would have taken it from a graffiti. We must say whoever traded it was quoting Bergson. In the Bergsonian graffiti, we read, time is nature's way of keeping everything from happening at once. In Bergson's opinion, this sentence illustrates very well the residual function that time has in the metaphysics of the ancient as well as in the metaphysics of the moderns, including the metaphysics of the physics of relativity. In fact, in metaphysics, the only function of time, according to Bergson, is to delay a whole ideally already given to a superhuman intelligence, that is to say, to the complete science that we must suppose possessed by God. God, in fact, does not play dice. Time would therefore be, just as the ancient believed, the measure of our ignorance. Nothing but a blur, as Rovelli says. Here is the metaphysics of the physics of relativity, the natural metaphysics of the mind that speculates upon becoming. Liz Molin called this metaphysic of the physics of relativity the cosmological fallacy. The cosmological fallacy is the idea the whole is given. The whole is given, and if the whole is given, the science de facto suppose to its ground a complete ideal science de jure. Bergson, as a philosopher historian, sees here the function of the Aristotelian nous poietikos. For this science de jure, what is in succession for us is a timelessly present. In a certain way, everything has been consumed by this science. Everything has already been relegated to the past. Everything has already happened, and everything is given to an overflight look. For this science, the future has passed, and there is no surprise that one can play time travel. However, the delay takes another meaning if, with Bergson, it is not understood negatively, that is, metaphysically, time as a partial negation of the whole, but affirmatively. Then the delay becomes a process, the blur, a hesitation. The hesitation is not an oscillation between possibles, but a creation of the novelty, that cannot be reduced to the starting condition. Blur, is not a minus, but a plus of vision, as happens to artists who turn a defect of normal vision into a resource. For example, El Greco's severe astigmatism. In the blur, we see more. We expand our perception by extending it to what escapes us in the normal perception. The normal perception is the pragmatically oriented perception. What do we extend it to? We extend it to the interval. According to Bergsonian empiricism, our concrete experience is not marked by intervals. It is made up of intervals. Recall that after relativity, the interval is no longer space but time. It is distance. It has time. The interval is the effectiveness of time. Intervals, Bergson continues, means indeterminacy in things, de l'indétermination dans les choses. Oh, that locative is very important. In things, not of things. Dans les choses, non des choses. It means that indeterminacy is the effectiveness, the Wirklichkeit of the real, and is not contingency. Bergson himself struggled a lot to free his philosophy from contingency. We will not be able to verify it now, but the Bergsonian philosophy of the nature is not, as many believe, and among these we must perhaps include Bergson. Bergson himself is not a metaphysics of contingency. To sum up, for Bergson, the whole is not given. The whole is as all taking place. It happens. Thus, no proposition better expresses the metaphysical conception to which Bergson has strenuously opposed throughout his life than that which can be read in Arthur Eddington's book on relativity and which Bergson extensively mentions. Eddington says, events do not happen. They are just there, and we come across them. The formality of taking place, and Eddington puts this sentence between quotation brackets, the formality of taking place is merely the indication that the observer has, on his voyage of exploration, passed into the absolute future of the event in question, and it has no important significance. It is completely the metaphysics of the physics of relativity. Against this metaphysics, Bergson never tires of reiterating that time is real because it acts, because it has effects, because it does something. Time causes. However, we must read correctly this statement, time causes. For Bergson, causation is time itself. Duration is creative. If time flows in short blocks or drops, as William James said to challenge Zeno of Ilea, every drop is the whole of the reality that takes place. Whitehead will confirm that the Bergsonian duration, correctly understood, is not a continuity of becoming, but becoming of continuity. There are only real pulsations. Bergson had not, in Matière Mémoire, in Introduction à la Métaphysique, Bergson had not in fact spoken of a single real duration, but of a multiplicity of coexisting duration, each of which is a determinate consciousness. How to reconcile, then, this thesis with the claim of a unique time in ds, the material time, unique, universal, impersonal, of which Bergson is a champion in ds, and which drew criticism to him. Bergson, in fact, seems a retrograde, almost a supporter of the Newtonian image of the universe. But this material time, unique, universal, impersonal, is made possible by coexistence of these drops of duration in the simultaneity of flow. In principle, explains Bergson, nothing excludes that we can suppose a simultaneity of flow in which all durations coexist, although proceeding at different rhythms, a kind of conscience of all consciences. Bergson writes, thus is born the idea of a duration of the universe, that is to say, of an impersonal consciousness that is the link among all individual consciousness as between that consciousness and the rest of the nature. End of quotation. This impersonal consciousness, this supreme simultaneity of flow, is the condition of possibility of translation projection of the duration of the universe in linear time, which, according to common sense, extends endlessly from the past to the future. The unique time of common sense is not a mistake. It is an image in the Bergsonian sense, approximate like all images, but founded in the thing. It's an image of the real consciousness that is the very core of the experience. We cannot speak of reality that endures without, says Bergson says, inserting a consciousness into it. Quanto tempo ancora? The model proposed by Bergson to interpret the paradox of twins is the perspective representation, the Albertian pyramid. Peter is a real observer, a motionless reference system who actually takes the measurement of its system. And Paul is an observer that Peter represents as real. To whom are given by him, by Peter, certain measures attributed by transformation according to a certain rule of the measures that he himself took. We know what happens. Time dilatation, simultaneity that becomes succession, and length contraction. Paul on the projectile is like Paul at a distance reduced by Peter, the painter who paints it according to a strictly perspective criterion. Its shrinkage is not real, but it records correctly the distance from Peter to Paul. From Paul to Peter. What is then the relationship between Peter and Paul? It is the relationship of the referent to the referred. We can use, to explain this relationship, we can use the categories of Benveniste linguistics in this regard, and we can say that they are in the relationship of the subject of the enunciation to the subject of the statement. The subject of enunciation is the self that says I. It is not the same of the subject I of the statement. The first one is the referent, the second one, the referent subject. However, according to the Bergsonian interpretation of relativity, the relationship between referent and referred is a relationship of absolute reciprocity, bilateral, not unilateral, that must verify the invariance of a system of relations. According to Bergson, interpreting relativity philosophically means to claim firmly the perfect reciprocity of rectilinear uniform motion. Once the hypothesis of stationary ether has been dissolved, the relativity of motion is absolute. Relativity of motion is the Cartesian thesis, the Galilean thesis that only Einstein demonstrated. Bergson says, but the doing away with, or to get rid of, the privileged system is the very core of the theory of relativity. Herein lies the essential difference with Newton's physics. For the Newtonian physics, an absolute privileged reference system is given, an absolute quiet and absolute motions. The difference between the philosopher and the physicist consists then in the greater or lesser fidelity to the hypothesis of a universe without a privileged reference system. The philosopher can make it his own unconditionally. The physicist cannot do it. The idea of reciprocity of motion is, Bergson says, philosophical and no longer physical. The physicist must decide for a reference system because he must measure, because he must represent, because he must give a configuration to the universe. Projecting the universe onto a piece of paper is immense ethical responsibility. Writes, no physics, no astronomy, no science is possible if we deny the scientist the right to represent the whole universe mathematically on a piece of paper. If there is a privileged system, then there will be multiple times. There will be Paul Dwarf, who, if he left the picture, if he returned from his interstellar journey, would remain dwarf next to Peter. But if there is absolute reciprocity, the hypothesis of multiple time, faster and slower, is valid only according to the referent relationship, according to the subject of enunciation, subject of the statement relationship. There are so many times because there is a unique time in which all times are given. So, in DS, we witness a passing of the baton of the hypothesis of relativity from the physicist to the philosopher. This is why the philosopher adds two additional arrows to Einstein's train skip. The philosopher places himself by the thought at one and the same time, put in italics by Bergson, on the track and in the train. Drawing this graph, Bergson writes, we have refused to turn physicist. His problem is not the mathematical configuration of the universe on a piece of paper, according to laws of mathematical perspective. His purpose is the intuition of the real in its difference of kind from the virtual. What is real then? We have a first answer. I would call it the phenomenological answer because it is the same response as the coeval Husserlian phenomenology. Real time is lived time, perceived time, indecompressible time. We have to wait for the sugar cube to melt in the water. Real is the proper time of the reference subject and not the phantom time of the reference subject. Real is the time of the conscience, meaning by this word the subject of the enunciation. Real is an axial present, as Benveniste calls it, a fake present, a present that does not pass, but in which everything passes and through which everything can pass. We are not saying that Peter is real and Paul is imaginary, but that there is real time where there is a memory at work. The clocks suppose it in order to serve as clock that indicate the time. Memory means time to the first person, not necessarily a human person. You know that Bergson, just like the shamans, includes in the grammatical category of the first person every living being, and wonders if it is possible, on the basis of the Alexander's dictum, that there is something real that is not a living being, that is not agent, capable of producing effect. As we have already seen, nothing prevents us, at least in principle, from extending this living present to the whole universe, which thus becomes the ultimate subject of the enunciation, the last referent, the very first person, although for us, the maximally impersonal. There is real time only when there is an absolute present that serves as a foundation. This answer, first answer, recalls the paradoxical thesis of Husserl in 1934. We, the German philosopher writes, never abandon the earth, even when we go to the moon. On the moon, after all, one lands. To exist means to be an immobile reference system. But we have also a second answer that takes into account the radical reciprocity of movement. After all, the phenomenological answer is one-sided. It assumes that the subject of enunciation enjoys absolute immobility. It is the immobility of the transcendental subject, not measurable as such, but condition of all measurements. Bergson instead claims that the philosopher is left with the burden, with the task, with the responsibility of bringing the thesis of the relativity of motion to its extreme consequence. The phenomenological answer told us under what condition the physical configuration of the world is given, that is, measurement of time. But the philosopher is such because it does not choose by making his own and completely Einstein's idea of reciprocity. If choosing is mathematizing, if choosing is configuring, not choosing is intuiting. Not choosing is to grasp real time in its making, is to move from the plane of the configured world to that of its event, from the given, the factum, to the giving of the given, to the theory. What is real for the poor philosopher who thinks with relativity? Real is the absolute of the passage, the third time, the absolute of the passage, the change as substance. Real is the interval. Real is not the fact, but the act, the activity that does the fact. This activity, this energia, this Wirklichkeit is exactly the theme of our ghost story. Is the incessant doubling of Peter in Paul. Not Peter and Paul, or even Peter instead of Paul, but becoming Paul of Peter, and becoming Peter of Paul. The interval between Peter and Paul is real, even more real than Peter and Paul. So, the Bergsonian intuition takes us into a radically relativistic universe, in which the phenomenon, Paul, cannot ignore the observer, Peter, and in which the observer, Peter, ceases to be a spectator to become part of the phenomenon itself, to become Paul. No clock outside the universe. Bergson calls it creative progress. Deleuze says open hole. Time is a simple and indivisible act. Its essential characteristic is the paradoxical coupling of continuity and heterogeneity. It is in fact continuous to the extent that is heterogeneous and vice versa. Discussing in his book different symbolic system, Bergson always returns to his fundamental idea. Duration as multiplicity of interpretation, distinct from homogeneous time as a multiplicity of juxtaposition. What is this difference? In a multiplicity of interpretation, the subject of change is not given, is not a thing, is not a fact, is not a substance, but it is built in the process itself, and it is a fact, this one of which one cannot overestimate importance, and it is inseparable from the acts that put it in place. Paul exists only as long as Peter looks at him, and Peter is immobile only by convention, by decision, because he looks at himself as an identity. So he too is a ghost in a relativistic completion universe. In fact, we had said at the beginning of our speech that it was enough for Paul to return Peter's gaze so that Peter suddenly, immediately became a ghost. Paul looks him and Peter becomes a virtual being. Now we can point out that Paul's petrifying gaze is nothing but the gaze that Peter turns to himself when he looks at himself watching. It is enough that Peter sees himself see, and the Peter seen becomes a ghost, for the Peter is his. What is real then? For the philosopher who takes Einstein's relativity seriously, real is the constantly changing relationship of Peter and Paul, or of Peter with himself. Real is the relationship between Peter and Paul, or of Peter with himself. Real is the interval that cannot have another consistency than in a given configuration of the universe in the measurements, but which cannot be reduced to any of those measurements. It is not localizable. Criticizing the metaphysics of the physics of relativity, Bergson alludes to another physics, a truly relativistic physics, where Peter and Paul are intertwined or entangled in an inseparable embrace that cannot be located in space and time, here and now, because of space-time. That entanglement is the real foundation. Thanks. Chiedo a Donatella di venire. Sì.
Possiamo fare domanda in inglese? No, vieni? No, come facciamo? Domanda in inglese? No, domanda in inglese, poi rispondi in italiano e traduciamo la risposta. Mauro? No, domande in inglese. No, o traduciamo. Vieni qua, dai, come vuoi.
I was trying to think about a way to formulate my question in French, but I'm too bad in French. Give me 5 minutes and I can do that. I agree with you, there is a metaphysics that is read superficially from physics, as if you could derive a metaphysics from physics, which is not the case. But here we have another metaphysics, which is Bergson's metaphysics. So how do we choose between them?
No, è vero, noi abbiamo un'altra metafisica. La metafisica bergsoniana vorrebbe essere
un empirismo radicale, questa è la sua specificità, no? Si propone come il tentativo di un empirismo radicale, cioè di non trascendere in alcun modo i dati dell'esperienza. Come empirismo radicale e come vorrebbe essere in qualche modo un passo fuori dalla storia della metafisica, nella misura in cui tutte le metafisiche, compresa la metafisica della relatività, sono caratterizzate dalla fallacia, dalla fallacy of misplaced completeness, no? Cioè dalla fallacia della concretezza malposta, cioè sono caratterizzate dal fatto di trascendere sistematicamente l'esperienza e di spiegare l'esperienza a partire da una dimensione supplementare. Quindi la mia risposta è vero, è un'altra metafisica, è una metafisica dell'esperienza pura. Bergson è un empirista radicale, un empirista, vuole essere un empirista radicale e proprio in quanto empirista vuole abbandonare le secche della metafisica degli antichi come della metafisica dei moderni, che è caratterizzata appunto dal trascendere l'esperienza in direzione di un concetto che la spiega.
Grazie.
So you said that it's true that we have two kinds of metaphysics, but the fact is that Bergson is a radical empiricist in this. So he wants to be quite close to the experience as it is, so to get out from the mud of classical metaphysics, if I'm getting it right.
Giuseppe, and then...
Can you elaborate more? Let us better understand what is this tissue of coordination of duration, this parallelism of flows in the philosophy of Bergson. Because again, of course, it's the point for Einstein that he doesn't like, but Hermann Weyl neither, and he was very close to Einstein. So this is maybe an answer, but tell us more.
Come sanno tutti coloro che hanno frequentato Bergson, la filosofia, la metafisica bergsoniana, appunto l'empirismo puro di Bergson, è un monismo e un pluralismo al tempo stesso, no? E questo si vede molto bene proprio a proposito della nozione di durata, no? Cioè per Bergson non si dà una durata, si danno costantemente una molteplicità di durate, ogni durata è una memoria, cioè una coscienza in atto, ma le molteplicità di durata suppongono al loro fondamento la possibilità della loro coesistenza in una durata delle durate, che Bergson pone sempre in un certo senso. Bergson è un filosofo profondamente ispirato da Plotino e che riprende proprio un po' lo schema neoplatonico. Queste molteplicità di durate convivono e le dobbiamo supporre fondate in una durata ultima, che è una durata di tutte le durate, che rappresenta in qualche modo lo stato embrionale della materia, ecco, lo stato embrionale dell'universo. Quindi ogni durata è una coscienza, ogni organismo può essere pensato come una pluralità di durate, no? E quindi anche come una concorrenza di questi ritmi di durata. E non c'è quindi un monismo, non c'è ma c'è una radicale posizione di tipo pluralistico da questo punto di vista di Bergson. Chiaramente queste durate, la cosa importante, queste durate non sono necessariamente delle coscienze umane, cioè è riduttivo pensare l'analogia durata-coscienza in chiave antropomorfica, cioè durata, coscienza, uomo, non sono la stessa cosa. Ovunque c'è una memoria al lavoro c'è una coscienza in atto. Questa è la tesi bergsoniana, che può essere assimilata a quella panpsichista per certi aspetti, eccetera, però questa è la tesi bergsoniana. Ovunque c'è vita in atto, c'è coscienza, perché ci deve essere, cioè c'è una memoria elementare, cioè ci deve essere, ovunque c'è vita in atto ci deve essere un rapporto tra il prima e il dopo. Se non c'è questa memoria elementare in atto non c'è vita.
Okay, so basically he says that the metaphysics of Bergson defends both the monism and the pluralism at the same time, and you have multiplicity of durations, and each duration is a consciousness in out. And so you have a coexistence of consciousness And but there is
each one will.
And you have a duration of all the durations. Am I right to say something like this? And but there is just one fundamental duration, which is the embryonal state of the universe. And it doesn't need to be anthropomorphic metaphysics, because you just need a memory, and it can be a memory. You need memory in order to have life, but it doesn't have to be an anthropomorphic metaphysics.
Maybe you?
Yeah, just one comment, and maybe I'm curious to see whether this is relevant for some of the discussion you made. I was struck by the quotation you gave about the dialogue between Einstein and Bergson about the radical wish of removing any privileged reference frame. This is a topic already came out earlier this morning, and I just wanted to comment that something that maybe at that time was not so clear is that indeed, in a very real sense, in today's cosmology, relativistic cosmology, we do have a privileged rest frame. You know, the cosmic microwave background allows any cosmic observer to measure the age of the universe just by measuring the temperature, or to measure the velocity with respect to this cosmic reference frame. And in fact, we use this, we can measure the rotation of the Earth around the Sun by looking at the Doppler effect compared to the CMB photons. So, in a very real sense, things have changed, and the expansion, in fact, is what fixes, somehow, something that is not completely, let's say, observer-dependent. So I don't know, in that light, what this discussion could tell us, you know, which, you know, Einstein himself resisted very much the idea of expansion. Or of a beginning of time, for example. So it's interesting to see the historical perspective, how things have changed.
Sì, grazie. Grazie per la domanda. Molto brevemente, l'ipotesi bergsoniana è che il sistema, cioè non si possa far scienza senza un sistema di riferimento privilegiato, quindi cioè, per misurare occorre supporre un sistema di riferimento, quindi non è possibile fare scienza senza questa supposizione. La differenza tra filosofia e fisica inizia per Bergson proprio su questo punto, proprio perché non ha più bisogno il filosofo, nell'ipotesi bergsoniana, di misurare. Non perché non riconosca, come si dice spesso, no? Non riconosca le misure del filosofo, la classica storiella della differenza tra qualità e quantità, per cui Bergson sosterrebbe che la durata è qualitativa e quindi essendo qualitativa non può essere misurata. Cioè non c'è nessuna ostilità da parte di Bergson nei confronti della scienza, ma assolutamente. Bergson voleva essere, da un certo punto di vista, voleva produrre i concetti adeguati per la scienza del suo tempo, insomma questo ormai è fuori discussione. E non c'è nessuna ostilità nei confronti della scienza, c'è l'idea che il compito della scienza non sia il compito del filosofo. Cioè il compito della scienza assolutamente fondato, cioè la scienza tocca l'assoluto per Bergson, lo dice in diversi luoghi, cioè la scienza ha a che fare con l'assoluto. Non è che abbia a che fare col relativo, ha a che fare con l'assoluto. Allora, però il compito della scienza e il compito del filosofo sono diversi e sono perfettamente complementari. Questo era il sogno di Bergson, no? Proprio la totale complementarità di filosofia e di scienza. Il compito, detta molto brevemente, l'ora è tarda, mi perdonerete l'estrema brutalità dell'affermazione, detto molto brevemente, il compito della scienza è misurare. E in questo non ci sono alternative al discorso scientifico. Il compito della filosofia non è misurare. Il compito della filosofia è intuire, e intuire vuol dire Per Bergson non tanto avere un colpo di pistola e mentare, insomma, avere l'insight nella verità, no, intuire vuol dire creare cioè essere isomorfi con il proprio pensiero al processo con il quale la natura si fa, cioè produrre un isomorfismo tra il pensiero e l'essere. Perché il nostro pensiero è altrettanto naturale di tutti gli altri fenomeni della natura. Quindi se la scienza ha il compito di misurare e coglie un assoluto, il compito della filosofia non è misurare ma intuire, e intuire vuol dire spostarsi dal piano del dato, del fatto, al piano dell'atto. Ora, atto e fatto non sono tra di loro due realtà metafisiche separate, sono implicate necessariamente l'uno nell'altro. Questo il filosofo, lo scienziato non lo può fare, lo può fare il filosofo, ma si tratta sempre per entrambi di stare nel reale cogliendo il reale da due punti di vista diversi. Sì.
Correct me if I'm wrong. According to Bergson, you cannot do science without a privileged
System.
And but the philosopher doesn't need to measure because that's the task of the physicist, of the scientist.
E le sue misure sono misure della realtà, non sono misure di fantasmi.
Sì, the measurement is the measure of reality.
Yeah.
And this is the difference between science and philosophy. So science has the task to measure, and philosopher has the task to have intuitions. And but still science has to do with absolute. But let's say that science and philosophy have just two different perspectives and two different tasks when it comes to reality. And the philosopher wants to produce an isomorphism between thought and being. And basically I think that, and they are complementary. I mean,
We got 3 more questions. The first one, second one, and the last one.
Too much.
Troppe. Tardi.
This is lunchtime. She never spoke. Okay. Okay. I have technical questions. Thank you so much for this great talk. In your opinion, is it correct to say that for Bergson, Einstein's extraordinary discovery is the relativity of the rhythm of time and not the relativity of time as a qualitative becoming? So,
le risponderei di sì, cioè io credo che veramente Bergson sposi completamente la relatività di Einstein, cioè la sposa completamente. E credo che veda nella relatività di Einstein in qualche modo la verifica anche sul piano scientifico di quella che era stata la sua intuizione di una molteplicità di durate coesistenti a ritmi diversi. Ma filosoficamente si rende conto che per parlare di molteplicità bisogna supporre un'unità di fondo, perché altrimenti non ci sarebbero molteplicità, cioè non c'è molteplicità senza un'unità di fondo presupposta. Però io credo, ripeto, che ci sia veramente questa adesione incondizionata di Bergson alla relatività. Immagino anche il suo stupore, cioè quando lui ritira il libro non è la risposta, ma la risposta è già data, ma quando lui ritira il libro dalla circolazione, perché lo ritira? Attenzione, non lo ritira perché lo contesta, lo rifiuta, tant'è vero che nel 1920, poi nel 1930, cioè scusate, nel 1930 e poi nel 1934, nella nota alla Pensée Mouvant, ritorna su questo libro sostenendone integralmente le tesi, quindi non è che lo ritiri perché lo ritira perché non ne poteva più di questo equivoco che si era creato, che lo contrapponeva agli scienziati, che faceva di lui il campione dell'anti-intellettualismo, che faceva di lui il filosofo irrazionalista, che si opponeva il filosofo retrogrado, eccetera. Quindi è questo equivoco che è la ragione del ritiro del libro dal piano editoriale.
So Bergson likes and worships Einstein's relativity, but philosophically speaking, he realizes that in order to have multiplicity, you need to have a fundamental unity of reality. That's the
last
The question concerns the sort of underdetermination in physics, moving and building on the radical empiricism of Bergson. You quoted Zapek, who wrote a couple of very different books on Bergson,
Modern Physics.
Also, there was another book on the philosophy and factor, many papers. The idea of Will Zapek that and he endorsed completely his radical criticism of Bergson, is that relativity proposes an ontology in which is not time that is spatialized, but on the contrary, it is space that is something dynamics. He says that it is not possible to observe what is outside our life cone, and so we can say that in a certain sense it is radical empiricism. This is not something real. What is outside our life cone is completely unreal. And so in a certain sense, all this time, all this movement. On the contrary, there is a very important treatise which you know very well and better than me, in Italy on Bergson philosophy, it is written by Mathieu, and he interprets Bergson and relativity in a different way, in the sense that relativity concerns what happened at the level of the most superficial, because it's the idea in the interpretation of Mathieu or some philosophy of a sort of series of layers, and relativity concerns the most superficial layer, and concerns time completely spatialized. On the contrary, something that comes more and more, it is moving in the direction of the deep or awareness of our mind. So the interpretation is different. It moves on the same basis that is radical empiricism, but in a certain sense, Zapek gives a lot of importance to relativity and observation. On the contrary, Mathieu gives a lot of importance to our inner experience, and the conclusion is quite different about relativity.
Sì, lei ha perfettamente ragione, ci sono due modi di interpretare la cosa che sono ben rappresentati da queste due posizioni, Capek e Mathieu, in quel bellissimo saggio tra l'altro su Bergson. Io concordo molto di più con Capek che con l'interpretazione di Mathieu, come del resto è il risultato anche da quello che provavo a dire, e mi pare che la cosa fondamentale che coglie Capek è che, che paradossalmente la relatività sarebbe stata la migliore alleata di Bergson. È la migliore alleata di Bergson, nella misura in cui dissolve che cosa? Dissolve l'idea dell'istante, dissolve l'idea del presente puntuale come atomo irrelato sul quale si erano costruite tutte le metafisiche del tempo, e ripropone al posto di questo atomo irrelato, un presente inteso come campo di presenza, cioè un presente spesso, un presente soprattutto che non passa, perché tutto quello che passa deve passare attraverso di lui. Allora, Capek lo dice con una formula molto bella, dice non ci sono più distanze spaziali, no? Una volta che noi assumiamo la tesi relativista non ci sono distanze spaziali, tutte le distanze sono tempo. Tutte le distanze, anzi se c'è una space-like vuol dire che non c'è rapporto, che c'è una contemporaneità che significa assenza di rapporto. Ecco, questa mi pare l'intuizione potente della metafisica bergsoniana, no? Cioè, in questo modo si restituisce al tempo l'efficacia, cioè il tempo fa qualcosa, ma fa qualcosa proprio nella misura in cui è un intervallo, proprio nella misura in cui dura. Quindi da questo punto di vista mi pare che appunto Bergson trovava nella relatività einsteiniana, anche in questa sua forma radicalizzata, un alleato per questa nuova concezione del tempo.
Okay, so you said that he agrees with the question. It feels much more sympathetic with Capek than Mathieu, because Capek stresses more than relativity was the best ally for Bergson, because it solves, it evaporates the problem of the instant, proponing the present as a field of a present, so giving back to time a sort of efficacy. So, let's start.
Yes, yes, but maybe later because somebody. So we've got one. Thank you, Rocco. There is catering for lunch